Hello there, and welcome to Science for Sleep, where we take some of the biggest questions in science, give ourselves plenty of time to explore them, and hopefully become a little more relaxed in the process. Tonight, we are going to look at something that is happening to you right now, although there is absolutely no reason to be alarmed by it. You're moving through space at an extraordinary speed. Of course, that statement alone is not particularly surprising. We all know that Earth rotates. We know that Earth travels around the Sun. Most of us have also heard that the Sun moves through the Milky Way. Nothing in space seems especially interested in sitting still, but the movement we are interested in tonight is larger than all of those motions. The entire Milky Way, along with the other galaxies in our local neighbourhood, is moving through the universe, and when astronomers began carefully measuring that motion, they found something unusual. Our part of the universe appeared to be heading strongly in one particular direction. For a long time, the obvious explanation was that something massive ahead of us was pulling us toward it. That would make sense. Gravity pulls matter toward other matter. Put enough galaxies, galaxy clusters, gas and dark matter in one region of space, and neighbouring galaxies will gradually accelerate in that direction. Astronomers did indeed find enormous concentrations of matter in roughly the direction of our motion. Names such as the Great Attractor and the Shapley concentration entered the story, and they will become important later. Then researchers tried looking at the problem from the other direction. Instead of asking only what might be pulling us from ahead, they asked what was happening behind us. And there, in a region of the universe containing far less matter than average, they found evidence for something that behaves, mathematically, rather like the opposite of an attractor. It became known as the Dipole Repeller. That name makes it sound rather dramatic, as though there might be some enormous invisible machine sitting hundreds of millions of light years away, pushing galaxies across the cosmos. Fortunately, there is no evidence of a cosmic leaf blower pointed at the Milky Way. The real explanation is stranger in a quieter way. The Dipole Repeller appears to be associated with a vast underdense region, a place where there is less matter than the cosmic average. Because gravity is produced by matter, a region with relatively little matter does not pull on its surroundings as strongly as denser regions do. When astronomers reconstruct the motion of galaxies around such an underdensity, the galaxies appear to stream away from it. So the word repeller is useful, but it can also be slightly misleading. The void does not appear to possess some new form of anti-gravity. It is not actively shoving the Milky Way away like someone making room for themselves on a crowded sofa. Instead, the uneven distribution of matter throughout the universe produces an imbalance in gravitational attraction. Dense regions pull strongly. Empty regions contribute much less pull. When you map the resulting motion, the underdense region behaves as though it were pushing things away, and apparently we are one of the things moving away from it. Before we go any farther, where are you listening from tonight? Perhaps you're in bed with the lights already off. Maybe you're listening from a sofa and telling yourself you'll move to bed eventually. Perhaps it is late evening where you are, or very early in the morning, or possibly the middle of the afternoon, and you're simply someone who enjoys hearing about enormous cosmic structures while everyone else is being productive. Whatever the case, have you ever stopped to think about which direction you are moving through the universe? Not which direction your house faces, or which direction Earth is rotating, but the direction that our entire galactic neighbourhood is travelling. It is an odd question because we feel completely stationary most of the time. You can lie perfectly still in bed and have no sensation of astronomical travel whatsoever. Your pillow does not slide backward. Your glass of water remains where you left it. Nothing in the room suggests that you are participating in several different motions at once, yet you are. Earth rotates once roughly every 24 hours. Earth also orbits the Sun. The Sun, carrying Earth and the rest of the solar system with it, moves around the centre of the Milky Way. The Milky Way itself moves relative to nearby galaxies. Our local group of galaxies also has a measurable motion relative to the wider universe. Movement is layered on top of movement. That might sound as though we ought to feel permanently dizzy, but constant motion is not something your body can detect by itself. What you notice is acceleration, especially sudden acceleration. A smoothly moving airplane can feel almost motionless until it turns, climbs, descends, or somebody attempts to open a packet of crisps 3 rows behind you. The same basic principle allows us to travel with Earth without feeling its enormous speed. Astronomers, however, do not have to rely on what movement feels like. They can measure it. And one of the most useful things they can measure is something left over from the early universe, the cosmic microwave background. The cosmic microwave background, often shortened to CMB, is faint radiation that reaches us from every direction in space. It comes from an era when the universe was only about 380,000 years old, long before stars, planets, galaxies, late-night videos, or anyone worrying about whether they had remembered to charge their phone. The radiation is extremely cold today, only a few degrees above absolute zero, and across most of the sky it is remarkably uniform. But it is not perfectly uniform from our point of view. One side of the sky appears slightly hotter, while the opposite side appears slightly colder. This large-scale difference is called the CMB dipole. The simplest way to understand it is to imagine moving through a very light rain. Even if the rain is falling evenly, you experience more drops hitting your front than your back because you are moving into them. The rain has not suddenly developed a preference for one side of your coat. Your movement changes what you experience. Something similar happens with the cosmic microwave background, although instead of raindrops we are measuring ancient radiation. In the direction we are moving, that radiation is shifted slightly. In the opposite direction, it is shifted the other way. By studying this dipole, astronomers can determine the motion of our local group relative to the cosmic microwave background. And the number is not small. Our local group is moving at roughly 631 kilometers per second relative to the CMB. That is more than 2 million kilometers per hour. It would make the morning commute considerably shorter, although parking might become difficult. The local group includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and many smaller galaxies bound together by gravity. So when astronomers talk about this large-scale motion, they are not simply describing the Sun moving through our galaxy. They are talking about the motion of the entire galactic neighbourhood. That immediately raises a fairly obvious question. Why? If our local group has this additional motion through the universe, what caused it? Gravity is the natural place to look for an answer. The universe is not filled with matter evenly on the scales we see around us today. Galaxies gather into groups. Groups gather into clusters. Clusters are linked by enormous filaments containing galaxies, gas, and dark matter. Between those structures are great regions with far less matter, known as cosmic voids. Seen on the larger scales, the arrangement resembles a network. Astronomers usually call it the cosmic web. Our Milky Way exists inside this uneven landscape. It is therefore surrounded by gravitational influences coming from many directions at once. Imagine standing in the middle of a very large crowd while several people around you are gently pulling on ropes attached to your chair. If the pulls were perfectly balanced, you would remain in place. If more people were pulling strongly from one direction, however, the chair would begin moving that way. Gravity across the cosmic web works in a much more complicated three-dimensional version of that situation. Large concentrations of matter create stronger gravitational attraction. Regions with less matter create less attraction. The final motion depends on the combined effect of everything around us. For decades, researchers naturally concentrated on the crowded parts. One famous region became known as the Great Attractor. It lies hundreds of millions of light years away in the broad direction toward which many nearby galaxies appear to be moving. The name sounds almost suspiciously confident, as though astronomers had discovered the person responsible and were preparing to question them. In reality, the Great Attractor is a region associated with a large concentration of mass. it became central to attempts to explain the peculiar motion of our galaxy and its neighbours. But there was an observational problem. Part of that region lies in a difficult area of the sky from our point of view, obscured by the stars, gas and dust of the Milky Way itself. Trying to study distant galaxies through the dense central regions of our own galaxy is a little like trying to inspect the houses across the street while someone holds a glowing lampshade directly in front of your face. Over time, observations improved. Astronomers mapped more galaxies at greater distances. The picture became larger. Farther away, they identified the Shapley concentration, an enormous collection of galaxy clusters representing another major concentration of matter. Its gravitational influence appears to be significant when researchers reconstruct the motion of galaxies across our part of the universe. This helped, but it did not make the entire problem disappear. The exact motion of the local group was difficult to explain using visible concentrations of galaxies alone. There were debates over how much of our velocity came from nearby structures, how much came from more distant structures, and whether researchers had adequately mapped all of the matter responsible. One reason this was difficult is surprisingly simple. It is much easier to notice where the universe contains something than where it contains very little. A galaxy announces itself. It contains stars. Stars produce light. Gas can emit radiation. Galaxy clusters may contain hundreds or thousands of galaxies. Even dark matter, which does not shine, can reveal itself indirectly through its gravitational effects on visible objects. A huge empty region is different. A cosmic void does not provide you with a convenient collection of bright objects to photograph. Its defining feature is the comparative absence of matter. You recognize it largely because things are missing. That creates an odd observational bias. If you're trying to understand what is causing galaxies to move, you naturally look toward the places crowded with galaxies, because those are the places your telescope can map most easily. The emptier side of the gravitational equation can be much harder to see. This matters because the universe does not care whether something is convenient for astronomers to observe. If one side of our galactic neighbourhood contains a huge concentration of matter and the other contains an enormous underdensity, both sides affect the balance of gravitational forces. The dense region pulls more strongly. The underdense region pulls less strongly than an average region would. From our perspective, the combined result can look as though we are being pulled from one direction and pushed from another. That was the important change in perspective behind the Dipole Repeller research. In 2017, a team led by Yehuda Hoffman, working with Daniel Pomereda, Brent Tully and Hélène Courtois, published a reconstruction of the large-scale velocity field around us. Instead of relying only on maps showing where galaxies are located, they used information about how galaxies are actually moving. That difference is important. A map of galaxy positions tells you where the visible structures are. A map of velocities tells you something about the invisible gravitational landscape influencing them. Imagine watching leaves floating along a stream when you cannot see the shape of the riverbed underneath. The leaves turn, accelerate, gather and separate according to the flow of water. By carefully measuring their movement, you could begin inferring features you cannot directly see. Galaxy motions can be used in a related way. Astronomers measure the distances to galaxies and compare those distances with the galaxy's observed redshifts. Cosmic expansion gives galaxies a general tendency to recede from one another, with more distant galaxies usually showing larger recession speeds. But galaxies do not simply follow that expansion perfectly. They also have what astronomers call peculiar velocities. Despite the name, a peculiar velocity is not a galaxy doing anything especially eccentric. It simply means motion relative to the smooth expansion expected from the universe as a whole. Those additional motions contain information. Galaxies fall toward concentrations of matter. They move away from underdense regions as matter drains toward denser surroundings. By collecting enough measurements and reconstructing the three-dimensional flow, researchers can infer the gravitational terrain around us, including terrain that is difficult to observe directly. The team used galaxy distance measurements from the Cosmic Flows 2 dataset and a statistical reconstruction technique to estimate the velocity and density fields across a huge region around the local group. What appeared was a striking pattern. On one side lay the influence of a major attractor associated with the Shapley concentration. On almost the opposite side was a region from which the reconstructed flow diverged. The researchers called it the Dipole Repeller. Their analysis suggested that the attraction associated with Shapley and the effective repulsion associated with this underdense region made roughly comparable contributions to the large-scale motion connected with the CMB dipole. That is the part of the story that makes the dipole repeller so interesting. For years, the intuitive question had been, what is pulling us? The newer picture asked us to consider a second question at the same time. What are we moving away from? It is worth being precise here because the phrase "something is pushing the Milky Way" can easily create the wrong picture. There is no known mysterious force emerging from the dipole repeller. There is no evidence that gravity suddenly changes its rules inside a cosmic void. Ordinary gravity is enough. Consider two sides of a balance. If matter were spread perfectly evenly around us on very large scales, gravitational pulls from different directions would tend to cancel. But matter is not spread perfectly evenly. Suppose there is much more matter in one direction and much less in the opposite direction. The stronger gravitational influence comes from the crowded side. You then accelerate away from the emptier side. Mathematically, when scientists reconstruct the velocity field, that underdense region behaves like a repelling source. This is why researchers can speak of a repeller without claiming the discovery of anti-gravity. It is a description of the flow, and what a flow it is. Our galaxy is not making this journey by itself. Nearby galaxies participate in large-scale patterns of motion, produced by the distribution of matter across hundreds of millions of light-years. Entire groups and clusters drift through a cosmic landscape that has been developing for billions of years. The origins of that landscape reach back to the early universe. Matter was once distributed far more evenly than it is today. There were small differences in density from place to place. Some regions contained slightly more matter, others contained slightly less. Gravity amplified those differences. Areas that began a little denser attracted more material. Over immense periods, they developed into galaxies, clusters, superclusters, and filaments. Regions that began slightly emptier lost matter to their surroundings and became increasingly underdense. Voids grew. So when we talk about the dipole repeller, we are not describing a recent event that suddenly began moving the Milky Way. We are looking at the result of structure formation operating across cosmic history. The flow we participate in today is connected to differences that developed over billions of years. There is something slightly amusing about discovering that our galaxy has been travelling through the universe under the influence of enormous structures that humanity did not even know existed until very recently. For most of history, the Milky Way was simply the pale band across the night sky. Then we learned that we lived inside it. Then we learned that it was a galaxy. Then we discovered other galaxies, then galaxy groups, then clusters, then superclusters, filaments, walls, and voids. Every time astronomers increased the scale of the map, our cosmic address acquired another line, and now even the motion of that address has a story. If you happen to be lying perfectly still while listening to this, it is worth enjoying the contradiction for a moment. You may be motionless relative to your mattress. Your mattress is moving with Earth. Earth is moving around the Sun. The Sun is moving through the Milky Way. The Milky Way is moving with the local group, and the local group is travelling at hundreds of kilometres every second relative to the cosmic microwave background. You do not need to do anything about this. There is fortunately no need to fasten your seatbelt. The motions are part of the stable gravitational environment in which we have always existed. But understanding them requires astronomers to answer a question that becomes surprisingly difficult once we begin thinking carefully about it. When we say that the Milky Way is moving at hundreds of kilometers per second, moving relative to what? There is no painted grid across space. There are no stationary signposts floating between galaxies. Earth moves relative to the Sun moves relative to nearby stars, The Milky Way moves relative to Andromeda. The local group moves relative to more distant galaxies. Different reference frames give us different descriptions of motion. The cosmic microwave background gives cosmologists something unusually useful, because it provides a reference connected to the large-scale universe. That is why the dipole matters so much. It gives us evidence that our local group has a substantial peculiar velocity relative to that cosmic frame. To understand that gravitational geography, the first useful fact is that the Milky Way has never been sitting quietly in one place. It only appears that way because we are travelling with it. When you look up at the Milky Way from a dark location, assuming you are fortunate enough to be somewhere without too much artificial light, it can seem almost permanent. The same broad band of stars returns night after night. Constellations keep roughly the same shapes during a human lifetime. Nothing about the view suggests that the entire structure is moving through space. That sense of stillness is mostly an accident of perspective. We are inside the thing we're trying to watch move. If you were sitting inside a large airplane travelling smoothly at cruising speed, you could look around the cabin and see people reading, sleeping, drinking coffee, or attempting the difficult task of opening a tiny packet of pretzels without firing them into the next row. Everything inside the aircraft would appear reasonably stationary relative to everything else. Looking out the window would reveal a different story. Something similar happens on a much larger scale with the Milky Way. Earth, the Sun, nearby stars, distant stars, clouds of gas, dark matter, and the galaxy itself are participating in different layers of motion. Because we share many of those motions, they are not immediately obvious to us. Start with the movement closest to home. Earth rotates on its axis. At the same time, it travels around the Sun. The Moon travels around Earth while accompanying Earth around the Sun. The Sun itself is not waiting patiently at the centre of all this. It is travelling through the Milky Way together with the rest of the solar system. Our solar system is located tens of thousands of light years from the galactic centre, in the region commonly called the Orion Spur or Orion Arm. From there, the Sun travels around the Milky Way at roughly 828,000 kilometers per hour, and one complete orbit takes about 230 million years. That means the last time the Sun occupied roughly the same position in its galactic orbit, Earth looked very different. Dinosaurs were around. The continents were arranged differently. There were no cities, roads, telescopes, alarm clocks, or people lying in bed listening to someone discuss galactic dynamics. One trip around the Milky Way takes so long that the entire recorded history of human civilization occupies only a tiny fraction of one galactic year. Even that orbit is not quite as simple as the diagram you might remember from school, where the solar system is represented by a neat dot circling a neat galactic centre. The Milky Way is a complicated gravitational system containing hundreds of billions of stars, large clouds of gas, stellar remnants, and a much larger halo of dark matter. Stars do not move as though they are attached to a solid rotating disk. The Sun follows an orbit produced by the combined gravitational field of the galaxy. It also moves slightly up and down relative to the main galactic disk and has additional motion relative to nearby stars. So even before we ask whether the Milky Way itself is travelling anywhere, our own movement inside it is already complicated. This creates an important problem. If you measure the motion of something from Earth, part of the motion you observe may belong to that object, but part may come from you. Suppose you are sitting on a train and another train passes your window. For a brief moment, especially if you cannot see the station, it can be surprisingly difficult to tell which train has started moving. Your visual system sees relative motion. It does not automatically provide you with a label saying, your train is stationary and the other one is moving at precisely 27 kilometers per hour. Astronomy faces a much larger version of the same problem. Movement needs a reference frame. You can describe Earth as moving around the Sun. You can describe the Sun as moving relative to nearby stars. You can describe the Milky Way relative to Andromeda. You can describe the local group relative to more distant galaxies. None of these descriptions is automatically the one true cosmic motion. They answer different questions. This is one reason saying, the Milky Way is moving at this speed, can be misleading unless we immediately add, Relative to what? Within our local neighbourhood, the Milky Way belongs to a gravitationally connected collection of galaxies called the Local Group. The Local Group contains the Milky Way, Andromeda, Triangulum, and many smaller galaxies. These objects are not simply being carried apart by the general expansion of the universe. On this comparatively small scale, their mutual gravity matters enormously. Andromeda provides the most famous example. The galaxy is currently approaching the Milky Way, rather than simply receding from us with cosmic expansion. Both galaxies are massive members of the same gravitationally bound group, and their relative motion is part of the internal dynamics of that system. So already we have several different kinds of movement. The Sun goes around the Milky Way. The Milky Way and Andromeda move relative to one another. Smaller galaxies orbit and interact with the larger ones. The entire local group has another motion relative to structures outside it. Trying to combine all of that into one simple arrow would be rather like trying to describe the movement of a passenger walking down the aisle of a train while the train crosses a rotating Earth that is orbiting the Sun. You can certainly calculate it, but the first question still has to be, which motion are we interested in? For the Dipole Repeller, the movement we care about is not the Sun's orbit around the Milky Way. It is not primarily the Milky Way's movement toward Andromeda either. We are interested in the motion of our wider galactic neighbourhood relative to the large-scale universe. That brings us back to the cosmic microwave background. The CMB gives astronomers a particularly valuable reference because it comes from the early universe and surrounds us in every direction. If we were perfectly at rest with respect to that background, after accounting for small primordial variations, its average temperature would look essentially the same in opposite directions. That is not what we observe. There is a strong dipole pattern. One broad side of the sky is slightly warmer and the opposite side slightly cooler. The standard interpretation is that this is mainly produced by our motion relative to the CMB rest frame. After the motions internal to the solar system and galaxy are accounted for, astronomers infer that the local group is moving at about 631 kilometers per second relative to that cosmic reference frame. The uncertainty quoted in the Dipole Repeller analysis is about 20 kilometers per second. 631 kilometers every second is difficult to picture. During the time it takes you to take a slow breath, our galactic neighbourhood travels thousands of kilometers relative to the CMB frame. In a minute, the distance becomes tens of thousands of kilometers, yet nothing on your bedside table moves. That is because speed alone does not produce the sensation of movement. You and everything nearby are participating in the motion together. The more interesting question is where that 631 km per second motion came from. It cannot be explained merely by saying, the universe is expanding. Cosmic expansion and peculiar velocity are not the same thing. On sufficiently large scales, distant galaxies generally separate as space expands. The farther away a galaxy is, the larger its cosmological recession tends to be. This overall relationship is part of what astronomers mean when they discuss the expansion of the universe. But galaxies also respond to local and regional gravity. Imagine placing small marks on a slowly stretching rubber sheet. As the sheet stretches, the marks move apart. Now imagine that some of the marks also begin sliding across the surface because there are slopes or forces affecting them locally. The stretching represents the general expansion. The additional sliding represents peculiar motion. The analogy is imperfect, as rubber sheet analogies usually are once they have been asked to explain too much physics, but the distinction is useful. A peculiar velocity is simply an object's velocity relative to the smooth motion expected from cosmic expansion. The local group has one. Many other galaxies and galaxy clusters have them as well. These peculiar motions are incredibly valuable because gravity produces them. Matter is distributed unevenly through space. Galaxies respond to that distribution. If you can measure enough galaxy motions, you can work backward and learn something about the gravitational structures producing them. This is where the Milky Way stops being merely our home galaxy and becomes something more useful scientifically. It becomes a test particle, not literally of course. A galaxy containing hundreds of billions of stars is not what a physicist would normally describe as a small experimental object. But in the context of the cosmic web, its movement provides information about the gravitational field around us. Our galaxy is falling through a landscape shaped by matter. So are neighbouring galaxies. The direction and speed of that fall tell us something about the landscape itself. Gravity has been influencing these motions for billions of years. Slightly over-dense regions in the early universe attracted additional matter. As material accumulated, their gravitational influence grew. Those regions eventually produced galaxies, galaxy groups, clusters, and larger structures. Underdense regions developed differently. Matter tended to move out toward denser surroundings, allowing the underdense regions to become larger and emptier. The result today is a universe filled with enormous differences in density. There are crowded knots containing galaxy clusters. There are filaments stretching between them. There are broad sheets and walls, and between them are voids containing far fewer galaxies. The Milky Way sits inside that network rather than outside it. Our immediate surroundings are themselves structured. The Milky Way and Andromeda belong to the local group. The local group sits within a larger region containing nearby groups and clusters. The Virgo cluster, for example, has long been recognized as one important source of gravitational influence in our neighborhood. However, Virgo cannot explain our full large-scale peculiar motion. Neither can any single nearby object. An analysis of local peculiar motion published by R. Brent Tully and colleagues separated the local group's movement into contributions arising on different scales. It identified motion away from the nearby local void, attraction associated with the Virgo region, and a still larger component connected to more distant structures. Their components collectively related to the same roughly 631 km per second motion seen in the CMB dipole. This tells us something important about the journey of the Milky Way. There is no single engine driving it. No enormous object has attached an invisible rope to the galaxy and started towing it through space. Our movement is the accumulated result of gravitational influences acting across different distances and in different directions. Nearby structures matter. Distant structures matter. Regions containing extra matter. Regions missing matter too. If that sounds difficult to untangle, that is because it is. An astronomer trying to explain the Milky Way's peculiar velocity cannot simply point a telescope in the direction of motion and look for the largest visible object. The gravitational field depends on mass, including dark matter. Some important regions are partially obscured by our own galaxy. Some influences originate hundreds of millions of light-years away. And because gravitational effects arrive from many directions, different contributions can add together or partially cancel one another. Imagine being in the center of a room while dozens of weak fans blow toward you from different directions. If every fan were identical and symmetrically arranged, the air currents might balance. Turn several fans off on one side, strengthen a few on the other, and place a very powerful fan near one corner, and a net airflow develops. You could measure that flow where you are standing. Then you could try to infer the arrangement of fans from the movement of the air. Cosmologists face something conceptually similar, except the room is hundreds of millions of light-years wide. Many of the fans are invisible, and nobody was thoughtful enough to leave an instruction manual. The direction of our motion offered an obvious clue. For much of the 20th century, astronomers mapped galaxies in and around that direction and found major concentrations of matter. One of them was the region that became associated with the Great Attractor. The term Great Attractor can give the impression of one gigantic object, perhaps a single supercluster waiting in the darkness and pulling everything toward it. The actual situation is more complicated. It refers to a region of enhanced mass concentration associated with a broader network of galaxy clusters and structures. Nearby galaxies show coherent motions indicating gravitational attraction toward that general part of the sky. This seemed promising. If the local group is moving rapidly in one direction, and there is an enormous concentration of matter in roughly that direction, perhaps the mystery is solved. Unfortunately, the universe rarely arranges its difficult problem so politely. Measurements showed that structures beyond the traditional Great Attractor region also mattered. One of the most significant is the Shapley concentration, a particularly rich concentration of galaxy clusters located much farther away. As surveys expanded and velocity reconstructions improved, researchers found that our local flow had contributions extending to very large distances. Earlier reconstruction work showed how difficult it was to make the predicted gravitational dipole fully line up with the observed CMB dipole using only mapped galaxy concentrations within more limited volumes. That mismatch kept the problem interesting. You might think astronomers would simply survey farther and farther until every source of gravitational attraction had been catalogued. In principle, that helps. In practice, there are two problems. The first is that mapping matter becomes harder with distance. The second is that attraction is only half of the story. Consider a simpler situation. Imagine that you are standing between two identical groups of people, pulling on you with ropes. 10 people pull from the left and 10 from the right. If everyone pulls equally, you remain roughly where you are. Now remove 8 people from the group on the left. You begin moving toward the right. Someone watching only the right side might say, "Those 10 people are pulling you toward them." That is true, but it is not the complete explanation for why the forces became unbalanced. The missing pull from the left matters too. This is the conceptual doorway into the Dipole Repeller. Cosmic voids are not sources of a new repulsive force. Gravity has not changed direction inside them. Instead, they contain less matter than average, so the gravitational attraction coming from those directions is weaker. Meanwhile, matter around the void tends to fall toward surrounding denser structures. Viewed as a velocity field, galaxies flow away from the underdense region. This can be mathematically represented as a repelling influence. Before researchers could confidently identify such an influence at large distances, however, they needed good measurements of galaxy velocities, and measuring those velocities requires more than simply obtaining a redshift. Redshift tells astronomers how much the wavelength of light from a galaxy has been stretched toward the red end of the spectrum. In the nearby universe, redshift includes contributions from cosmic expansion and from the galaxy's peculiar motion. To separate those effects, astronomers also need an independent estimate of the galaxy's distance. If you know approximately how far away a galaxy actually is, you can calculate the recession speed expected from cosmic expansion. Then you compare that expectation with the observed redshift. The difference provides information about peculiar velocity. Do this for one galaxy and you have one useful measurement. Do it for thousands of galaxies distributed across the sky, and you begin building a map of cosmic flow. Those maps do not show galaxies simply travelling in random directions. Patterns emerge. Galaxies stream toward dense structures. Other regions show divergent flow. Large volumes of space participate in coordinated movement. The local group itself participates in a bulk flow extending well beyond our immediate neighbourhood. The Dipole Repeller study describes the local group's CMB relative velocity as part of a coherent bulk flow measurable to very large distances, emphasizing that the cause cannot be understood by studying the Milky Way in isolation. That is why the phrase, "the Milky Way is moving through space," is both correct and incomplete. The Milky Way is moving, but it is moving with companions. Andromeda shares much of our large-scale motion. Other nearby galaxies share it too. Groups and clusters over a considerable volume participate in related flows because all of them occupy the same large-scale gravitational environment. You could think of leaves travelling along different parts of a wide river. Individual leaves may swirl around one another, one may drift toward another, some may become temporarily trapped in small eddies. Yet the whole group can simultaneously be carried downstream. The Milky Way's interaction with Andromeda is one local motion. The local group's movement relative to neighbouring structures is another. The broad cosmic flow revealed by the CMB dipole is larger again. Keeping those scales separate prevents an easy misunderstanding. Andromeda approaching us does not mean the Milky Way cannot also be moving rapidly through the larger universe. Both things can happen at once. If two passengers walk toward each other inside a moving train, they are approaching one another while both remain passengers on the train. Galaxies are considerably less likely to ask who has seat 14B, but the principle works. Another useful consequence of this layered motion is that there is no need to imagine the Milky Way ploughing through a stationary substance filling space. The galaxy is not a ship crossing some universal ocean that defines absolute rest. Modern cosmology does not give us a simple universal floor against which every object's true speed can be measured. Instead, astronomers select useful reference frames. For large-scale cosmic motion, the CMB rest frame is one of the most useful. Against that frame, our local group has a clear and substantial velocity. That velocity has a direction. Once astronomers knew both, they could start asking what distribution of matter would produce it. For years, much of the attention naturally went toward what lay ahead. That is reasonable. If you drop a ball and it accelerates downward, you look below it for the massive Earth, rather than searching the ceiling for an absence of matter. The same intuition encouraged astronomers to search for attractors. The Great Attractor became part of the explanation. The Shapley concentration added another major source of attraction farther away. Yet the full three-dimensional velocity field contained information that a simple map of bright galaxies could easily hide. Galaxies were not only converging toward dense regions, they were diverging from underdense ones, and the local group happened to lie in a particularly interesting position within this uneven gravitational landscape. One side of the larger flow pointed broadly toward some of the richest concentrations of galaxies in our cosmic neighbourhood. Look in almost the opposite direction, however, and the map became much less crowded. That emptiness was not merely blank space on an unfinished survey. It could be dynamically important. The Milky Way's lack of stillness was therefore telling astronomers more than where we were going. It was giving them information about places containing comparatively little matter, places that are naturally harder to find because they do not announce themselves with thousands of bright galaxies. The clue had been present in the motion all along. To recognize it, astronomers needed something better than an ordinary map of where galaxies were located. They needed a reference that could tell them exactly how our neighbourhood was moving in the first place, and for that, they turned to the oldest light we can observe. And that oldest light gives astronomers something unusually useful. It gives us a way to compare our motion with the universe on a scale far larger than the Milky Way, the local group, or any nearby cluster of galaxies. The cosmic microwave background is often described as the afterglow of the Big Bang, which is a convenient description as long as we remember that it was not produced at the instant the universe began. For the first few 100,000 years, the universe was filled with hot, dense plasma. Electrons moved freely among atomic nuclei, and photons repeatedly collided with those charged particles. Light could not simply travel across enormous distances as it does through space today. The early universe was effectively opaque. As expansion continued, the universe cooled. Roughly 380,000 years after the Big Bang, conditions became cool enough for electrons and nuclei to form neutral atoms. With far fewer free electrons available to scatter photons, radiation could finally travel much more freely. The light released during that transition has been moving through the universe ever since. Expansion has stretched its wavelengths enormously, reducing its effective temperature to about 2.7 Kelvin and shifting most of it into the microwave part of the electromagnetic spectrum. That radiation surrounds us. It does not come from a single object somewhere beyond the Milky Way. There is no CMB lamp at the edge of the observable universe sending microwaves toward us. We see the radiation arriving from every direction because wherever we look, we are looking back toward regions of the early universe from which that ancient light has had enough time to reach us. This makes the CMB very different from most things astronomers observe. Look toward the moon, and you are looking at one particular object. Look toward Andromeda, and you are looking at one particular galaxy. Point a microwave telescope in almost any direction, after carefully accounting for foreground radiation, and behind the stars, dust, gas, galaxies, and radio sources is the cosmic microwave background. It covers the sky. That makes it extremely useful when you want to answer a question about motion. Imagine being in a car on a foggy day. You cannot see buildings, road signs, or distant mountains. If the fog were perfectly uniform and there were no other clues, working out your motion might be difficult. But suppose the fog itself somehow produced measurable radiation, and your movement through it caused the radiation ahead of you to look slightly different from the radiation behind you. You would suddenly have a reference. The CMB does something rather similar. If our solar system were at rest with respect to the large-scale reference frame defined by the cosmic microwave background, the average temperature of that radiation would be almost identical in every direction, apart from the much smaller temperature variations created in the early universe. But we are not at rest. When astronomers map the microwave sky, one broad direction appears slightly warmer, while the opposite direction appears slightly cooler. That is the CMB dipole. The word dipole simply describes a pattern with two opposite sides. One side is shifted toward a slightly higher temperature, and the other toward a slightly lower temperature. The temperature difference is extremely small in everyday terms. The modern measured amplitude of the solar CMB dipole is about 3,362 microkelvin, or roughly 0.00336 Kelvin. Yet compared with the much smaller primordial CMB fluctuations that cosmologists normally study, the dipole is enormous. NASA's Lambda archive attributes this dipole primarily to the motion of the solar system relative to the CMB rest frame. The reason motion changes what we see is the Doppler effect. You have experienced a version of the Doppler effect with sound. An approaching ambulance has a siren that sounds higher in pitch than it does once the ambulance has passed and begins moving away. The siren itself has not suddenly changed its mind about what note to play. Relative motion changes the frequency you receive. Light behaves differently in detail, but relative motion also changes its observed frequency. Moving toward incoming radiation shifts it slightly toward higher frequencies. Moving away shifts it toward lower frequencies. With the cosmic microwave background, that creates a temperature pattern. The direction toward which the solar system is moving appears hotter. The direction from which we are moving away appears colder. So the universe has provided us with something that functions surprisingly well as a speedometer. It is not a speedometer attached to the Milky Way. There is no enormous dial floating above the galactic center, which is probably fortunate because astronomers would immediately argue about who was responsible for calibrating it. Instead, the CMB gives us a reference against which motion can be measured. Planck measurements and other analyses place the solar system's speed relative to the CMB at about 369 km per second, in a direction corresponding approximately to galactic longitude 264 degrees and galactic latitude 48 degrees. Planck also detected the expected effects of this motion through additional distortions known as aberration and modulation, providing another check on the interpretation of the dipole as a velocity signal. 369 km per second is already impressive. It means that relative to the CMB frame, the solar system covers a distance roughly comparable to the width of a large country in only a few seconds. But that number is not yet the velocity we ultimately want. Remember the problem from before. The Sun is moving inside the Milky Way. Earth is moving around the Sun. The Milky Way has its own motion within the local group. So the solar system's CMB dipole includes several motions layered together. Astronomers have to separate them. Earth's orbit provides a particularly neat example of how this works. As Earth moves around the Sun during the year, its orbital velocity sometimes adds slightly to our motion relative to the CMB and sometimes subtracts from it. That creates a small annual change in the observed dipole. WSMAP used this known orbital modulation as part of the calibration of its measurements, because Earth's orbital motion is accurately known. In other words, the CMB is sensitive enough that Earth's annual trip around the Sun leaves a detectable signature in the microwave sky. That alone gives a sense of how precise these measurements have become, but astronomers can keep correcting, remove Earth's motion around the Sun, account for the Sun's movement relative to nearby stars, account for the Sun's orbit within the Milky Way, then consider how the Milky Way moves relative to other members of the local group. Once those internal motions are separated from the larger movement, researchers can estimate the motion of the local group as a whole, relative to the CMB. That is where the larger figure enters the story. The dipole repeller analysis gives the local group velocity relative to the CMB as 631, plus or minus 20 kilometers per second. This is why you may sometimes encounter two apparently different cosmic speeds associated with the microwave background. One source may say roughly 369 kilometers per second. Another may say roughly 631 kilometers per second. Neither necessarily contradicts the other. The first usually refers to the motion of the solar system relative to the CMB. The second refers to the motion of the local group after accounting for important local motions inside our galactic neighbourhood. It is the 631 km per second local group motion that becomes especially important when we start asking what large-scale structures are influencing us. That distinction can be easy to miss because we live inside every one of these moving systems. You are moving with Earth. Earth is moving with the Sun is moving with the Milky Way. The Milky Way participates in the local group. The local group participates in still larger patterns of cosmic motion. There is no moment when one motion politely stops so that another can begin. They all happen simultaneously. Astronomers separate them mathematically because doing so allows each physical process to be studied. The CMB provides the large-scale reference needed to make those separations meaningful. There is another reason the microwave background is so useful here. The universe at the time the CMB was released was dramatically smoother than the universe we see around us today. Today, matter is strongly clumped. There are planets, stars, galaxies, clusters of galaxies, enormous filaments, large voids. The difference between standing inside a galaxy and floating in the middle of a major cosmic void is enormous in terms of local matter density. The early universe was much more uniform. The CMB does contain tiny temperature variations, generally around 1 part in 100,000, and those variations are extremely important. They trace small density differences that eventually grew through gravity into the large-scale structures we see today. Kobe established the CMB's extremely accurate blackbody spectrum and detected these small anisotropies. WMAP and Planck later mapped them in much greater detail. But the motion-induced dipole is much larger than those primordial fluctuations. That makes it stand out very clearly. Take one of the famous full-sky CMB maps produced by missions such as WMAP or Planck, and the colourful pattern usually shown to the public is not simply the raw microwave sky. Astronomers remove several things before producing the maps used to study primordial structure. They have to deal with microwave emission from our own Milky Way. They remove or model foreground sources. And importantly for our discussion, they normally subtract the large dipole created by our own motion. The final Planck CMB products, for example, have the monopole and dipole removed from the full-sky maps used for cosmological analysis. That is rather interesting when you think about it. For researchers studying the early universe, our motion is foreground contamination. It gets in the way. For researchers studying the motion of the Milky Way and the local group, that same contamination is the signal they want. One scientist's nuisance is another scientist's cosmic speedometer. The CMB dipole therefore plays two different roles depending on the question being asked. If you want to understand the early universe, you subtract it carefully. If you want to understand how we're moving through the present-day universe, you examine it carefully. What makes the second task especially interesting is that velocity is not just a fact about where we happen to be going. It contains information about gravity. The local group did not randomly decide to begin travelling at 631 kilometers per second. In the standard cosmological picture, peculiar velocities develop because matter is distributed unevenly. Regions containing more matter than average exert stronger gravitational attraction. Regions containing less matter than average contribute less gravitational pull. Over billions of years, galaxies respond to that uneven field. Their motions therefore carry information about the surrounding distribution of matter. Suppose you walked into a room and discovered a ball rolling steadily across the floor. Knowing its speed would be useful. Knowing its direction would be useful. But you would probably then start looking for a reason. Was the floor tilted? Had someone pushed the ball? Was there a magnet involved? Did a cat decide that astronomy required additional complications? The CMB gives cosmologists the equivalent of the ball's velocity. The next task is reconstructing the slope of the floor, and the direction is crucial. The hotter side of the CMB dipole tells us the direction of our motion relative to that background. Once corrections are made for the sun's local movement and the local group's internal dynamics, astronomers obtain an arrow describing the peculiar velocity of our galactic neighbourhood. Then they can compare that arrow with maps of the nearby universe. If gravity is responsible, there should be enough unevenly distributed matter to explain both the speed and the direction. At first, this seems like it ought to be a fairly simple exercise. Look in the direction we're going, find a very large concentration of matter, declare victory. The universe did provide a promising candidate. Actually, it provided several. The broad direction of our peculiar motion points toward a part of the sky containing major concentrations of galaxies and mass. This was encouraging because gravity gives us a straightforward prediction. If there is substantially more matter on one side of us than another, we should accelerate toward the more massive side. The problem is that gravity does not stop after the first convenient galaxy cluster. Every concentration of matter contributes. Nearby structures can pull strongly because they are close. More distant structures can still matter if they are massive enough. Dark matter contributes even though telescopes cannot see it directly. And empty regions change the balance by failing to provide the attraction that an average region would have supplied. The motion measured through the CMB is therefore the combined result of a three-dimensional distribution extending across an enormous volume. That became one of the central difficulties. How far away did astronomers need to map before the gravitational explanation matched the CMB dipole? If they mapped galaxies out to a certain distance and calculated their expected pull, would the resulting predicted motion point in the same direction as the observed one? Would its amplitude approach 631 kilometers per second? Or would important contributions continue appearing as the survey volume grew? For years, those questions produced complicated answers. Some of the local group's motion clearly originates nearby. Work on peculiar velocities has identified contributions associated with movement away from the local void and attraction toward the Virgo region, while a larger component appears on greater scales. Yet those nearby contributions do not account for everything. The CMB arrow continues pointing toward a broader gravitational problem. This is one of the reasons the dipole became so influential in studies of large-scale structure. It offered a target. Astronomers could build maps of galaxies, estimate the distribution of matter, reconstruct peculiar velocities, and ask whether the resulting gravitational flow converged toward the velocity independently measured from the microwave background. If it did, they had probably mapped the important structures. If it did not, something was missing. Surveys gradually reached farther, catalogues became larger, distance measurements improved, models became more sophisticated. The same basic question remained surprisingly stubborn. What is responsible for this motion? There is a small complication in calling the CMB a universal speedometer, because it should not be interpreted as proving that the cosmic microwave background defines absolute rest in the old Newtonian sense. Physics does not require a single privileged state of motion for all purposes. The The CMB frame is useful because the radiation is extremely uniform on large scales, and because cosmology provides a natural frame in which its dipole vanishes. You can choose that frame and say that an observer at rest with respect to it would see no motion-induced CMB dipole. That makes it enormously convenient for discussing large-scale peculiar velocities. But you have not discovered a secret stationary flaw beneath the universe. You have chosen a physically meaningful cosmological reference. That difference may sound technical, but it prevents a common misunderstanding. When we say the local group is travelling at around 631 km per second relative to the CMB, we're not saying it is breaking some universal cosmic speed limit for galaxies that are supposed to stay still. We are describing its motion relative to a particular large-scale frame. The question then becomes why our matter has that velocity in that frame. This is where the ancient universe and the modern cosmic web become connected. The CMB shows us the small density irregularities from which later structure developed. Gravity amplified those irregularities. Slightly denser regions accumulated more matter. Slightly emptier regions lost matter to their surroundings. Over billions of years, those tiny initial differences became the galaxies, clusters, filaments, and voids that now influence the motion of the local group. So the same radiation that gives us the velocity reference also contains evidence of the distant beginnings of the structures responsible for that velocity. The connection is not mysterious. It is simply gravity operating for a very long time. A small irregularity in the young universe can eventually become an enormous concentration of galaxies. Another small deficit can eventually become a cosmic void hundreds of millions of light years across. By the time humans appear with microwave detectors, computer models, and a strong desire to name large things dramatically, the original tiny differences have become a complicated gravitational landscape. Our galaxy is moving through that landscape. The CMB tells us how. Now imagine astronomers taking the local group velocity vector and placing it onto a map of nearby galaxies. The arrow points in a particular direction. Naturally, attention turns toward whatever lies ahead. There are galaxies there. There are groups. There are rich clusters. There is a complicated region partly difficult to observe because the plane of our own Milky Way blocks part of the view with stars, gas, and dust. That observational obstruction became especially frustrating because the direction of our large-scale motion passes uncomfortably close to this obscured part of the sky. Astronomers even have a suitably dramatic term for the hidden band, the zone of avoidance. The name does not mean spacecraft are forbidden to enter it. It means extragalactic astronomers traditionally had difficulty cataloguing distant galaxies there, because the Milky Way gets in the way. If you are trying to discover what is pulling your galaxy through space, having your own galaxy block, the view is a slightly inconvenient arrangement. Infrared, radio, and X-ray observations gradually allowed researchers to peer through more of the obscuring material. Behind it, the universe turned out to contain a major concentration of galaxies and mass. Galaxy motions in the surrounding regions seemed to converge toward it. For anyone trying to explain the CMB dipole, this looked extremely promising. The Milky Way and many neighbouring galaxies appeared to be streaming in roughly that direction. The object was not a single galaxy or even one ordinary galaxy cluster. It was part of a much larger gravitational region. And once astronomers realised how strongly our neighbourhood seemed to be responding to it, the name that attached itself to the mystery was almost inevitable. They called it the Great Attractor. The Great Attractor sounds like the sort of name astronomers might invent after running out of sensible options late at night. It suggests a single enormous object hiding somewhere beyond the Milky Way, pulling galaxies toward itself with irresistible gravity. For a while, that was not too far from the picture researchers were trying to build. The story began with motion rather than with something astronomers could photograph directly. During the 1970s and 1980s, increasingly precise measurements showed that galaxies in our region of the universe were not simply following the smooth expansion expected from the Hubble flow. They had additional peculiar velocities. Groups of galaxies appeared to be streaming together across an enormous volume of space. Our own local group was participating in that movement. The cosmic microwave background had already provided the most important clue. It showed that our galactic neighbourhood was moving rapidly relative to the large-scale cosmic frame. If gravity was responsible, there ought to be an uneven distribution of matter capable of producing that motion. Researchers therefore began measuring distances to galaxies independently of their redshifts. That distinction mattered, because redshift alone cannot always tell you exactly how a nearby galaxy is moving. Part of its observed redshift comes from the expansion of the universe. Another part can come from its peculiar velocity, the additional movement caused by local and regional gravity. If astronomers could estimate a galaxy's true distance using some independent method, they could calculate approximately how fast it should be receding because of cosmic expansion. They could then compare that expectation with the velocity indicated by its observed redshift. The difference revealed peculiar motion. Do this with a few galaxies and you get a collection of individual velocities. Do it with hundreds spread across a large region of the sky, and something much more interesting begins to appear. A flow. In one influential survey, astronomers studied hundreds of elliptical galaxies and found evidence for coherent motion toward roughly the same general region of the southern sky. The original Great Attractor model placed the centre of that flow in the direction of galactic longitude about 307 degrees and latitude about 9 degrees, at a scale corresponding to several thousand kilometres per second in Hubble flow distance. It was not initially a photograph of a single object. It was a gravitational explanation inferred from galaxy motions. That is worth keeping in mind because the name can be deceptive. The Great Attractor was discovered, in a sense, before astronomers could clearly see what was there. Imagine walking across a field at night while carrying a compass, except instead of the compass needle pointing north, it points downhill. You notice that water, loose leaves, and anything that can roll are all drifting in roughly the same direction. Even if darkness prevents you from seeing the landscape properly, you can infer that there is probably a depression somewhere ahead. The galaxy velocities were doing something similar. They were revealing gravitational terrain. Unfortunately, when astronomers looked toward the suspected region, they encountered one of the least cooperative parts of the sky. The Milky Way was in the way. From inside our galaxy, we see the galactic disk as a dense band stretching around the sky. It contains enormous numbers of foreground stars as well as clouds of gas and dust. Those materials make it difficult to observe distant galaxies behind the plane, particularly in visible light. This obscured region became known as the zone of avoidance. Again, astronomy does occasionally name things as though they belong in a fantasy novel. There is nothing physically dangerous about the zone of avoidance. Galaxies are perfectly capable of existing there. Astronomers simply avoided using that part of the sky in many early extragalactic surveys, because identifying distant galaxies through the foreground clutter was difficult. And, inconveniently, the suspected Great Attractor was located close to it. The situation was almost unfair. Astronomers had measured galaxies apparently streaming toward a particular region. Their calculations suggested that a great deal of matter should be present there. They pointed telescopes toward it, and our own galaxy effectively replied by placing a curtain across the window. Visible light surveys could still detect some structures around the edges, especially in the Hydra and Centaurus regions. But the central area remained poorly mapped. This raised an uncomfortable possibility. Perhaps an enormous amount of matter was hiding behind the Milky Way. If so, it might provide the missing gravitational pull needed to explain the strange motions. Fortunately, dust that blocks visible light does not block every wavelength equally. Infrared observations can penetrate dust more effectively. Radio telescopes can detect neutral hydrogen in galaxies, even when the same systems are difficult to see optically. X-ray telescopes can reveal hot gas inside massive galaxy clusters. As astronomers began studying the zone of avoidance using these other methods, the hidden extragalactic landscape gradually emerged. One object became particularly important. The Norma cluster, also catalogued as Able 3627, lies at low galactic latitude deep in the Great Attractor region. Detailed studies have shown it to be an extremely massive nearby galaxy cluster, with dynamical analyses placing its mass around the scale of a quadrillion suns within the region traditionally used to characterize the cluster. Its galaxy population and large velocity dispersion make it one of the most substantial known structures in that part of the local universe. Suddenly, the Great Attractor had something much more tangible associated with it. There really was a major cluster hiding close to the suspected location. Norma contains hundreds of galaxies moving within a deep gravitational potential. Much of the ordinary matter between those galaxies is heated to enormous temperatures and produces X-rays. Around and through the visible material lies still more mass in the form of dark matter. It is exactly the kind of place capable of influencing nearby cosmic motions. That does not mean Norma itself is the entire Great Attractor. This distinction matters. The Great Attractor is better understood as a broad gravitational region associated with structures including Norma, Hydra, Centaurus, surrounding filaments, and the larger mass distribution in that direction. In later velocity-based maps of our home supercluster, the Norma, Hydra, and Centaurus regions appear as part of the flow basin historically associated with the Great Attractor. A galaxy cluster may be one especially dense knot in that network, but gravity does not recognize the boundaries humans draw around catalogued objects. It responds to all the mass, galaxies, gas, dark matter, neighboring groups, filaments joining one concentration to another. Everything contributes. This helps explain why attempts to assign the Milky Way's motion to one convenient object became increasingly difficult. At first, the logic seemed attractive. We are moving in this general direction. There is a very massive region in this general direction. Gravity pulls. Problem solved. Except the numbers never behaved quite that neatly. Think about standing several meters from a large magnet while holding a collection of smaller magnets. If there are other magnets scattered around the room, your motion will reflect the combined influence of all of them. Finding one particularly strong magnet does not mean the others suddenly stop existing. The universe presents the gravitational version of that problem on a scale of hundreds of millions of light years. The Virgo cluster influences our neighborhood. The Great Attractor region influences it. Structures farther away influence it. Underdense regions influence the balance by contributing less attraction. The movement measured by the CMB dipole is the result of all of those contributions added together. There was another complication. If the Great Attractor were responsible for essentially all of the local group's large-scale motion, astronomers might expect the flow to settle around it in a relatively straightforward way. Galaxies on our side would fall toward it. Galaxies beyond it might show a corresponding pattern. Once researchers mapped far enough, the velocity field should reveal the destination clearly. But observation suggested that the flow continued on larger scales. The Great Attractor did not seem to be the end of the road. Some galaxies in and around the Great Attractor region themselves appeared to participate in a broader motion. That is a very important clue. Suppose you are standing on an airport moving walkway. You begin walking toward a person ahead of you. From your perspective, that person may look like your immediate destination, but then you notice that both of you are also being carried by the walkway towards something farther down the terminal. Your motion toward the nearby person is real. The larger movement is also real. Cosmic flows can be layered in a comparable way. Matter around the Milky Way can respond to relatively nearby structures, while the entire region simultaneously participates in motion, produced by more distant density variations. This was becoming apparent as surveys expanded. The Great Attractor clearly represented an important concentration of matter, but it could not comfortably carry the entire explanatory burden people sometimes placed on it. Even the Norma cluster illustrates the problem. Measurements of its distance and peculiar velocity found that Norma itself has only a small peculiar velocity relative to the CMB frame within the uncertainties, consistent with the idea that it sits near an important part of the Great Attractor flow. rather than simply being another object racing towards some hidden center nearby. That made the region scientifically important, but the broader question remained: what controls the full motion of the local group? To answer that, astronomers needed to stop thinking of the universe as a collection of isolated attractors and begin thinking in terms of a continuous velocity field. That change in perspective became particularly useful when researchers mapped what we now call Laniakea. Laniakea is a way of defining our home supercluster using galaxy motions rather than simply drawing boundaries around visible concentrations of galaxies. Researchers used peculiar velocity measurements to identify regions where galaxies tend to flow inward after the overall cosmic expansion and larger scale external motions are removed. They traced the boundaries where those flows diverge, somewhat like identifying drainage basins by watching where water would run across a landscape. Within that reconstruction, our local group belongs to an enormous flow basin roughly 160 megaparsecs across. The Virgo cluster, Norma, Hydra, Centaurus, the Pavo-Indus filament, and several voids all form parts of that larger structure. The word supercluster can sometimes make these structures sound more solid than they are. A galaxy is clearly an identifiable gravitational system. A galaxy cluster is also gravitationally bound in a fairly recognizable sense. A supercluster is more complicated. It is not necessarily one enormous object that will eventually collapse into a single structure. It can be defined according to galaxy density, connectivity, gravitational flow, or other criteria. Laniakea was specifically defined through peculiar velocities. Its name means something close to immense heaven in Hawaiian, but scientifically the important point is the flow. Our galaxy participates in that flow. When researchers visualize it, streamlines curve through the reconstructed density field toward regions of gravitational convergence. The Great Attractor occupies an important position within this local flow pattern. For a while, that picture made the Great Attractor sound almost like the bottom of our local gravitational valley. And on certain spatial scales, that remains a useful way to think about it. But scale changes everything. Smooth the velocity field over one distance and the flow may appear to converge toward Virgo. Smooth it over another distance, and a broader Hydra Centaurus or Great Attractor feature becomes apparent. Look on still larger scales and the influence of Shapley becomes more important. A 2026 reconstruction of the nearby universe made this point particularly clearly. Using constrained simulations of our cosmic neighborhood, researchers found that no single structure should be expected to dominate the entire local group velocity budget. Where reconstructed streamlines seem to converge depends partly on the spatial scale used to examine the flow. At smaller scales, Virgo becomes important. At intermediate scales, the Hydra Centaurus region appears prominently. At larger scales, the flow shifts toward Shapley. This does not mean the Great Attractor was a mistake. It means the original discovery was pointing towards something more complicated than the name suggested. The streaming motion was real. The mass concentrations were real. The hidden Norma cluster was real. The gravitational influence of the region was real. What changed was the idea that all of this could be reduced to one dominant object sitting at one location. Science does this fairly often. A simple explanation appears first because the available observations allow only a simple picture. Better data arrive. The simple picture does not necessarily disappear. It becomes part of a larger one. Newtonian gravity did not become useless when Einstein developed general relativity. The continents did not stop existing when plate tectonics explained how they move. And the Great Attractor did not vanish when astronomers discovered that our cosmic flow extends beyond it. It simply stopped being the whole story. There was also a more basic reason astronomers should have expected complexity. Gravity has no preferred stopping distance. The gravitational influence of an object weakens with distance, but a sufficiently massive structure farther away can still matter. If you double the distance to a particular object, its pull becomes weaker. But if the amount of mass also becomes enormously larger, the distant structure can remain significant. The universe contains concentrations on many scales. A nearby group may influence individual galaxies. A cluster can shape the motion of surrounding groups. A network of clusters and filaments can influence a much larger volume. So once surveys began revealing extremely rich structures beyond the Great Attractor, researchers had to include them in the calculation. One of those structures was already known from galaxy surveys. It lay farther away in approximately the same broad region of the sky. And it was enormous. The Shapley concentration contains a remarkable collection of rich galaxy clusters. Compared with the Great Attractor region, it is substantially farther from us, which weakens its gravitational effect. But the amount of matter concentrated there is so large that its influence can still reach our part of the cosmic web. This presented astronomers with a slightly awkward possibility. Perhaps the Great Attractor was not the final destination of the flow at all. Perhaps it was one major concentration along a much larger gravitational slope. To picture the difference, imagine watching water run downhill through a shallow basin. At first, you might notice a depression nearby and assume that all of the water is collecting there. Then a more detailed map reveals that the basin itself slopes toward a deeper valley farther away. The nearby depression still affects the water. It just does not determine the entire route. Something similar began happening to the Great Attractor. As surveys reached beyond it, the cosmic landscape opened up. The Hydra Centaurus region was no longer being considered alone. Astronomers could see richer concentrations farther out, with the Shapley region standing out as one of the most important. Modern reconstructions therefore tend to describe our peculiar velocity as the result of many gravitational contributions rather than a fall toward one hidden super-object. That is actually more consistent with what the cosmic web looks like. The universe is not arranged like a collection of isolated islands scattered through empty space. Galaxies gather along filaments. Filaments intersect at clusters. Clusters connect into larger complexes. Between them are voids. A galaxy moving through this environment is responding to the whole distribution. The Great Attractor became famous because it was one of the first places where that large-scale gravitational flow became impossible to ignore. It demonstrated that our local group was not simply drifting according to smooth cosmic expansion. Something in the distribution of matter was steering it. And because much of that distribution lay behind the Milky Way, the search forced astronomers to become increasingly creative about how they mapped the hidden universe. Infrared surveys helped reveal galaxies through dust. Radio observations traced hydrogen. X-ray astronomy revealed massive clusters through hot gas. Peculiar velocity surveys added another layer by showing how galaxies moved, even when the underlying matter distribution remained difficult to observe directly. Every method filled in another part of the map. The resulting picture was not a single monster hiding behind the Milky Way. It was a complicated section of the cosmic web. Norma sat inside it. Hydra and Centaurus were connected to it. Filaments extended through it. Nearby galaxies responded to it, and the entire arrangement belonged to a still larger pattern of motion. There is something useful about remembering how the discovery happened. Astronomers did not first find the Great Attractor and then notice galaxies falling toward it. They noticed the galaxies moving and inferred that an attractor ought to be there. Motion revealed mass. That same method will soon become important in the opposite direction. Because if you can infer a concentration of matter from galaxies flowing toward it, then you can also learn about an underdensity from galaxies flowing away. The equations do not require everything important to shine. For the moment, however, astronomers looking along the direction of our motion had an increasingly large amount of matter to consider. The Great Attractor had explained part of the original mystery, but farther along the same broad cosmic landscape stood a concentration so large that it changed the scale of the question. Instead of asking what was pulling us toward the Great Attractor, researchers had to ask whether the Great Attractor region was itself participating in a flow towards something farther away. The Shapley concentration sits much farther away than the structures traditionally associated with the Great Attractor, and that distance is one reason it took time for astronomers to appreciate how important it might be. If you could somehow look at the nearby universe from far outside it and remove the distracting glow of individual stars, you would not see galaxies scattered randomly. You would see them gathering into groups, clusters, long filaments, and dense intersections. Some parts of the map would look relatively quiet. Others would contain remarkable concentrations of matter. Shapley is one of the crowded places. It lies roughly in the same broad region of the sky as the Great Attractor, but considerably farther away. The main concentration is at a redshift of about 0.05 and includes a large complex of galaxy clusters connected by groups, galaxies, and filaments. Surveys of the region have shown that this is not simply one unusually large cluster. It is an extended overdensity containing many separate systems embedded in the same enormous structure. That distinction is important because gravity cares about the total distribution of matter. One galaxy cluster can contain hundreds or thousands of galaxies and a tremendous amount of dark matter. Put many such clusters close together, connect them with additional groups and filaments, and the resulting gravitational influence becomes much more significant. This is what makes the Shapley concentration stand out. Its central region includes famous clusters such as Albel 3558, Albel 3556 and Albel 3562, along with smaller groups and neighbouring systems. Studies of the central complex show evidence that these structures are interacting and dynamically active rather than simply sitting beside one another without effect. The scale is difficult to appreciate from a list of catalogue numbers. Albel 3558 does not sound particularly threatening. It sounds more like something you might find printed on the side of an office filing cabinet. But each one of those catalogue entries represents a major concentration of galaxies and mass, and they occupy a region where the density of matter is far above the cosmic average. A large redshift survey of Shapley collected more than 10,000 velocity measurements for more than 8,000 galaxies across a broad area of sky. It revealed that the main structure extends across tens of megaparsecs and includes not only galaxies inside rich clusters, but also a substantial population spread between those clusters. In that survey, nearly half of the observed galaxies associated with the Shapley region were outside the main cluster populations, emphasizing that much of the structure exists in the wider network between its densest knots. So when we talk about the gravitational influence of Shapley, we should not picture a single ball of matter. It is more useful to picture a very large region in which the universe has gathered considerably more material than average. That material includes stars, gas, galaxies, and especially dark matter. The stars provide the part we can see most easily, but they represent only a small fraction of the total gravitational budget. Hot gas inside galaxy clusters contributes additional ordinary matter, and dark matter provides much of the mass responsible for holding clusters together. Estimating the total mass of a structure this large is not simple. Researchers have approached the problem in several ways, and the answers depend partly on what boundary is drawn around Shapley. That is an unavoidable difficulty with superclusters. Unlike a planet or a star, they do not come with a sharply defined surface. One study based on the abundance of X-ray clusters estimated about 4.4 times 10 to the 16th solar masses within a sphere roughly 50 megaparsecs in radius centered on the Shapley supercluster. Other approaches have produced different values depending on the region included and the way unobserved matter is estimated. The important point is not one exact number. It is that the mass involved is measured in tens of quadrillions of suns when very large volumes around the concentration are considered. Even saying tens of quadrillions of suns barely helps. The sun is already massive enough to hold the entire solar system in orbit. Now imagine 1 million suns, then 1 billion, then 1 trillion, keep going. At some point, human intuition quietly leaves the room and mathematics has to take over. Shapley is useful precisely because it represents such an extreme overdensity on large scales. The central concentration was recognized long ago, but its relevance to our own motion became more interesting as astronomers realized that the Great Attractor might not explain the full velocity of the local group. Remember what had happened. Measurements showed that our galactic neighborhood was moving rapidly relative to the cosmic microwave background. Galaxy surveys then revealed coherent flows toward the Great Attractor region. A large amount of mass was found there, including the Norma cluster and the surrounding Hydra Centaurus structures. This explained an important part of the motion. But galaxies associated with the Great Attractor region did not all behave as though they had reached a final gravitational destination. Evidence suggested continued streaming toward greater distances. The question naturally shifted. If the Great Attractor is itself participating in a larger flow, what lies farther along that direction? Shapley was waiting there. Studies of peculiar velocities in the Great Attractor direction found that clusters lying between us and the Shapley concentration tended to have substantial peculiar motions consistent with flow toward Shapley. Type 1. A supernova measurements in the same broad direction supported the idea that the motion did not simply terminate at the Great Attractor. This changed the mental picture. Instead of imagining the Milky Way falling toward one large concentration, astronomers had to consider a series of structures extending across an enormous distance. Virgo affects us on relatively nearby scales. Hydra Centaurus and the Great Attractor become important farther out. Shapley lies farther away again. All of these gravitational influences overlap. It is a little like standing on a hillside containing several dips and slopes. If you release a ball, a nearby depression can alter its route even while the entire landscape slopes toward a deeper valley farther away. The local depression matters. The distant valley matters. The actual trajectory reflects both. This is why the term Great Attractor gradually became less useful, as a complete explanation for the local group's peculiar velocity. It remained a real and important gravitational feature, but researchers increasingly recognized that substantial acceleration could originate beyond it. A 2005 analysis using an all-sky sample of X-ray selected galaxy clusters estimated that about 44% of the local group's peculiar velocity in its model came from infall associated with the Great Attractor region, while about 56% came from more distant structures. Within that farther contribution, the Shapley supercluster stood out as the single most important overdensity in the sample, although other distant concentrations also contributed. Notice the wording there. The single most important overdensity, not the only one. This is a recurring theme in the story of our motion through space. Whenever one structure seems ready to become the answer, better maps reveal more participants. There is no cosmic tow truck pulling the local group from one convenient point. Gravity is being produced by an entire landscape. Still, Shapley was difficult to ignore. It is both very massive and located in a direction relevant to the CMB dipole. That combination made it an obvious candidate for explaining part of the remaining motion that could not comfortably be assigned to nearby structures. Astronomers sometimes describe gravitational effects by constructing a dipole from the distribution of galaxies or clusters. The idea sounds more complicated than it needs to. Imagine surrounding yourself with a map of matter in every direction. If the same amount of matter existed at similar distances everywhere, the gravitational influences would largely balance. But suppose one side of the sky contains many rich clusters, while the opposite side contains relatively little. The distribution now has an imbalance. That imbalance produces a preferred direction. Researchers can estimate the gravitational acceleration expected from the observed distribution and compare its direction with the velocity indicated by the CMB dipole. As surveys reached farther into space, the calculated gravitational dipole changed. New structures entered the map. Some strengthened the predicted acceleration, others altered its direction. Shapley produced a particularly noticeable effect because so much matter is concentrated there. This gave rise to a tempting explanation. Perhaps the local group is moving largely because Shapley is pulling us. There is truth in that statement, but once again it is incomplete. One difficulty is distance. Gravity weakens with distance. Shapley is extremely massive, but it is also hundreds of millions of light years away. A less massive structure close to us can therefore compete with a more massive structure located much farther away. Another difficulty is determining exactly how much mass Shapley contains. You cannot simply count the bright galaxies and multiply by an average value. Different regions contain different amounts of dark matter. Matter exists between the rich clusters. Surveys become incomplete at faint magnitudes. The boundary of the supercluster itself is not uniquely defined. Consequently, different studies have reached different estimates for how strongly Shapley contributes to the motion of the local group. For example, one analysis of the density contrast of Shapley estimated that the supercluster contributed only around 9% of the local group's peculiar velocity. That result was based on a particular model of its mass and density distribution. Other velocity field reconstructions have given Shapley a much more prominent role when considering the overall attractor associated with that direction. That disagreement is not a sign that astronomers have no idea what is happening. It reflects the fact that how much is Shapley pulling us is not as straightforward a question as it first appears. The answer depends on how the surrounding density field is reconstructed, how far the calculation extends, which observational data are included, and how structures are separated from one another. Gravity does not label its contributions. A photon arriving from a galaxy can tell us where that galaxy appears to be. A peculiar velocity tells us the combined gravitational effect of many structures. Separating that combined effect into neat percentages is something researchers do through models. It is useful, but nature itself is not assigning invoices. Still, by the time the Dipole Repeller research was carried out, the Shapley direction had become one of the major pieces of the puzzle. Using peculiar velocity measurements from the Cosmic Flows project, researchers reconstructed a three-dimensional velocity and density field around the local group. Instead of simply counting galaxies and asking where most of the light appeared, they examined the flow itself. That reconstruction identified a dominant attractor associated with the Shapley concentration. In the velocity field model, Shapley occupied the attracting side of a remarkably simple large-scale pattern. The word simple needs a little caution. The actual universe remains messy. There are many clusters, many filaments, many smaller voids, many local motions. But when researchers looked at the largest contribution to the flow relevant to the CMB dipole, much of the complexity could be summarized by two dominant directions. One pointed toward an attractor associated with Shapley. The other pointed almost the opposite way. At first, let us stay with the attracting side. A dense region pulls surrounding matter because gravity accelerates matter toward concentrations of mass. If Shapley contains considerably more matter than an average region of the same size, galaxies across a large surrounding volume will acquire peculiar velocities directed partly toward it. The effect is not instantaneous in the everyday sense. The present motions developed over cosmic time. The Shapley concentration itself grew because an initially overdense region attracted additional matter. Groups and clusters formed and merged. Filaments fed material into the dense environment. The gravitational field evolved along with the structure. Our local group has been responding to the larger density distribution over billions of years, so it would be misleading to imagine that Shapley suddenly turned on and began pulling the Milky Way last Tuesday. The motion we measure today carries the history of structure formation. Shapley is also useful because it demonstrates something that can be easy to forget when looking at pictures of galaxies. Space between us and a distant cluster is not irrelevant. The matter along the route contributes. The Great Attractor region lies in the foreground of Shapley. Other groups and filaments lie between and around them. The gravitational field therefore changes continuously, rather than jumping from one named structure to another. Names such as Virgo, Great Attractor, and Shapley help humans organize the map. The Milky Way responds to the map itself. There is an additional complication caused by cosmic expansion. A sufficiently distant structure is being carried away from us with the expansion of the universe, even while its gravity influences peculiar motions. That may sound contradictory, but the two effects can coexist. Imagine two objects on an expanding background while they also attract one another gravitationally. Their total relative motion depends on both the expansion and the additional velocity gravity produces. On small enough scales, gravity can overcome expansion completely. The Milky Way and Andromeda are an example. On larger scales, especially across supercluster-sized regions, expansion generally cannot be ignored. Shapley therefore does not have to be approaching us in order to pull us gravitationally in its direction. This is one reason phrases such as "we are falling towards Shapley" should be understood carefully. They refer to peculiar acceleration and velocity relative to the smooth Hubble expansion, not necessarily to an eventual meeting between the Milky Way and the entire Shapley complex. In fact, studies of Shapley's very large-scale density have found that while its central portions contain bound structures, the wider supercluster as a whole is not necessarily gravitationally bound against the accelerating cosmic expansion. So there is no need to worry that the Milky Way will eventually arrive at Shapley and discover that every parking space has been taken by a galaxy cluster. The important issue for us is its present gravitational contribution. Researchers can visualize that contribution using streamlines. In a reconstructed velocity field, a streamline shows the direction matter would move through the large-scale flow. Near an attractor, streamlines tend to converge. They come together because matter is falling toward an overdense region. Around a repeller, they diverge. That second behavior is where the story becomes much more interesting. If astronomers had only seen convergence towards Shapley, the broad explanation would have remained familiar. There is a great deal of matter over there. Gravity pulls us toward it. End of mystery. But the reconstructed flow did not merely show the local group heading toward a dense region. When researchers traced the velocity field backward, away from the Shapley side, they found that the flow appeared to originate from another broad region, on approximately the opposite side. That is an odd phrase. Flow originating from a region sounds as though something there is pushing matter outward. Under ordinary gravity, matter attracts matter. So what could produce a pattern in which galaxies seem to move away from one enormous area? The answer begins with something Shapley has in abundance. Matter, a great deal of it. Shapley matters because it contains far more matter than an average region of comparable size. Its gravity therefore pulls more strongly than an average patch of the universe would. Now reverse the situation. Suppose another enormous region contains far less matter than average. There would be fewer galaxies there, less dark matter, less total gravitational attraction. Matter near its boundaries would be pulled more strongly toward denser regions elsewhere. Over time, material would leave the underdense region and the void would grow. To an observer mapping only the resulting velocities, the pattern would look as though the empty region were pushing galaxies outward. And unlike Shapley, such a place would be unusually difficult to discover by simply counting bright objects, because the main thing defining it would be what was not there. That absence of matter is where the idea of a cosmic push begins to make sense, because a void is not simply a blank patch on a map. It is a region where the density of matter is lower than the average density of the surrounding universe, and that difference has consequences for how galaxies move. Cosmic voids are enormous. Some extend across tens or even hundreds of megaparsecs, occupying much of the volume between the denser filaments, walls, and clusters that make up the cosmic web. Although most of the galaxies and other concentrated matter live in those denser structures, a very large fraction of the universe's volume is taken up by underdense regions. If you have ever seen a computer simulation of the large-scale universe, you may remember the pattern. Bright knots of galaxies are connected by long filaments. Sheets of matter stretch between them. Large dark-looking gaps occupy the spaces in between. Those gaps are the voids. They are not completely empty. A cosmic void can contain galaxies, gas, dark matter, and other material. It simply contains much less of them than an average region of the same size. That distinction is important. When astronomers call something a void, they are not claiming that absolutely nothing exists there. Space has not been carefully vacuumed clean. The density is simply much lower than the cosmic average, and because there is less matter, there is less gravitational attraction coming from that direction. That is the beginning of the effect that can look like a push. Suppose you are standing between two groups of people, with each group pulling you using ropes. There are 10 people on your right and 10 on your left. Everyone pulls equally, you remain more or less in place. Now imagine that 8 people on the left quietly go home. Nobody on the right starts pulling harder. Nobody introduces a mysterious new force, but the balance changes. The 10 people on the right are now opposed by only 2 on the left, so you accelerate toward the right. Someone watching your movement might describe you as moving away from the left side. That's correct. They might even say that the left side is effectively pushing you away. That can be a useful description of the motion, but there is no actual person on the left pushing you. What changed was the imbalance between the pulls. Cosmic voids work in a related way. A region containing less matter than average produces less gravitational attraction than its surroundings. Matter near the void is pulled more strongly toward denser regions outside it. As a result, galaxies and other matter develop peculiar velocities directed away from the underdense region. In descriptions of the large-scale velocity field, an underdensity can therefore behave as a repeller. This does not require anti-gravity. It does not require negative mass. It does not require any new force pushing the Milky Way across the universe. Ordinary gravity is enough. The language becomes easier to understand if we go back to the early universe. When the cosmic microwave background was released, matter was distributed remarkably evenly compared with the universe we see today. But it was not perfectly even. There were tiny variations in density. Some regions contained slightly more matter than average. Others contained slightly less. Those small differences became extremely important because gravity amplified them over time. Consider a slightly overdense region first. Because it contains a little more matter, its gravitational pull is slightly stronger. It attracts additional material from its surroundings. That additional material increases the density. The increased density strengthens the gravitational attraction. Over billions of years, this process helps produce the dense structures we see today. Galaxies, galaxy groups, clusters, and the filaments connecting them. An underdense region develops in the opposite direction. Imagine an area that begins with slightly less matter than its surroundings. Because it is underdense, its gravitational pull is weaker. Nearby material feels a stronger attraction toward the denser regions around it, and gradually moves away from the underdensity. The region loses more material relative to its surroundings. Its density becomes even lower. The void grows. This is one of the basic ways the cosmic web develops. Matter tends to leave underdense regions and collect in sheets, filaments, and dense intersections around them. Cosmological models and simulations show that initially, underdense regions develop outward peculiar motions and can expand faster locally than the average Hubble expansion. There is a useful way to picture this without imagining that the void itself is producing a force. Think about a loaf of raisin bread expanding while it bakes. The bread itself expands and carries the raisins apart. That is the usual analogy for cosmic expansion. Now imagine that one area of the dough contains much less material than the surrounding regions, while other areas are denser. As the whole loaf expands, the local movement will not be perfectly uniform. Matter in the low-density region will tend to move outward relative to the average flow, while denser regions gather material. Eventually, a network develops in which the emptier regions occupy large volumes, and the matter becomes concentrated along their edges. The actual universe is three-dimensional, governed by gravity rather than baking, and thankfully contains fewer raisins. But the basic distinction between overall expansion and local peculiar motion is useful. A void does not simply ride along with cosmic expansion. Its underdensity produces additional motion relative to that expansion. Matter around it tends to stream outward. This makes void surprisingly important in cosmic dynamics. When we look at photographs or maps of the large-scale universe, our attention naturally goes toward the bright structures. Galaxy clusters are obvious. Thousands of galaxies packed together make an impressive photograph. A rich supercluster such as Shapley gives astronomers a large number of objects to detect, measure and catalogue. A void is visually less cooperative. Its most important characteristic is that many of those objects are missing. Trying to discover an enormous underdense region is therefore a bit like trying to identify which shelf in a library has lost the most books. The shelves containing thousands of books immediately attract your attention. The nearly empty shelf is easy to overlook unless you deliberately count what should have been there. This observational difference created an important bias in the search for the cause of the local group's peculiar velocity. Since the discovery of the CMB dipole, much of the attention naturally focused on overdense regions because overdensities contain galaxies, and galaxies produce light. Researchers could survey them. They could measure redshifts. They could identify clusters. They could estimate masses. They could say, there is a lot of matter in this direction, so it should pull us. That is exactly what happened with the Great Attractor and Shapley. But the gravitational balance does not depend only on where matter is abundant. It also depends on where matter is deficient. The team that identified the Dipole Repeller emphasized this point directly. Their analysis noted that underdense regions can contribute to peculiar motions just as overdense regions do, even though underdensities are much harder to chart because they contain relatively little light. There is an important subtlety here. Saying that an underdensity can push as much as an overdensity attracts does not mean gravity becomes repulsive inside a void. If you place two ordinary masses inside a void, they would still attract one another. A planet inside a void would still pull on a moon. A galaxy would still hold its stars. Nothing about Newtonian gravity or general relativity suddenly reverses. The repelling behaviour appears when we compare the gravitational influence of the underdense region with the average background and with denser regions around it. One way physicists handle this mathematically is by describing density contrast. Instead of asking only how much matter exists at a location, they ask how that density compares with the cosmic mean. An overdensity has a positive density contrast. An underdensity has a negative density contrast. When the peculiar gravitational field is calculated relative to the average expanding universe, an underdensity contributes an acceleration directed away from itself. That is why calling it a repeller is mathematically useful. Imagine a perfectly uniform universe for a moment. Matter is spread equally in every direction around you. Gravity from one side is balanced by gravity from the other. On large enough scales, there is no preferred direction for you to accelerate because the surrounding distribution is symmetric. Now remove a huge amount of matter from one side. The remaining matter on the opposite side has not changed. Its gravity is exactly what it was before, but the pull that previously balanced it has weakened. You begin accelerating away from the underdense side. From your position, it appears as though the emptier region is helping drive you outward. The effect becomes especially interesting when an underdensity lies roughly opposite a major overdensity. That produces an efficient gravitational arrangement. Imagine Shapley on one side containing far more matter than average. Then imagine a vast void on the opposite side containing much less matter than average. The overdense side pulls strongly. The underdense side provides much less opposing pull. Both differences contribute to motion in approximately the same direction. You are attracted from ahead and effectively repelled from behind. This is not two different forces. It is one gravitational field produced by an uneven distribution of matter. The distinction is similar to standing on a hill. You might say gravity is pulling you downhill. You could also describe yourself as moving away from the higher ground behind you. Those descriptions emphasize different parts of the landscape, but your motion comes from the overall shape of the gravitational potential. Cosmologists often use the idea of gravitational potential to understand large-scale flows. Dense regions behave like gravitational wells. Matter tends to move toward them. Underdense regions can be represented as higher regions in that effective potential landscape. Matter tends to move away from them toward the wells. The universe is not literally covered with hills and valleys, of course. You could not take a spacecraft to the edge of a void and discover that space had tilted. The landscape is a way of representing how gravity changes from place to place. It is especially useful because galaxy velocities trace that landscape. If many galaxies in one region are moving toward approximately the same location, astronomers have evidence for an attractor. If their velocities diverge from a region, that can indicate a repeller associated with an underdensity. This is where peculiar velocity surveys become more informative than ordinary maps. A standard galaxy survey tells you where galaxies are. A peculiar velocity survey also tells you how they are moving relative to the smooth expansion of the universe. Those motions contain information about matter we cannot easily see. That includes dark matter. It also includes the gravitational influence of underdense regions. The Dipole Repeller researchers used the Cosmic Flows 2 compilation of galaxy distances and peculiar velocities to reconstruct the three-dimensional velocity field around us. They applied a Wiener filter, a statistical method that helps infer an underlying large-scale field from noisy and incomplete observations. The details of the mathematics can become complicated quite quickly, but the purpose is straightforward. We cannot measure the full three-dimensional velocity of every galaxy directly. For distant galaxies, observations usually provide the component of peculiar velocity along our line of sight. Measurements also contain uncertainties. The distribution of measured galaxies is uneven. Some regions of the sky are better sampled than others. The reconstruction method uses those observations together with assumptions from the standard cosmological model to estimate the most likely large-scale velocity field consistent with the available data. Imagine trying to reconstruct ocean currents using thousands of floating buoys. Each buoy tells you something about the water around it. The measurements are incomplete. There are gaps between buoys. Some instruments are more accurate than others. Yet if enough observations are available, you can infer broad patterns in the flow. You may discover areas where currents converge. You may find other places where they spread apart. The Cosmic Flows data allowed researchers to do something conceptually similar with galaxies. They reconstructed streamlines representing the peculiar velocity field. Those streamlines revealed attractors where flows converged. They also revealed repellers where flows diverged. The researchers then examined the large-scale flow associated with the motion of the local group. What they found was striking because the flow could be described to a surprising degree by two dominant features. In one direction was the attractor associated with the Shapley concentration. In nearly the opposite direction was a major repeller. The Dipole Repeller analysis concluded that these two influences contribute roughly equally to the CMB dipole associated with the local group's motion. That is an extraordinary change from the older picture. Imagine spending years trying to understand why a boat is moving east. You investigate the current ahead. You study the wind. You identify a powerful flow drawing the boat eastward. Then someone measures the water behind the boat and discovers that a second large-scale flow is also carrying water away from the west. The original explanation was not wrong. It was incomplete. Shapley really does lie on the attracting side of the reconstructed flow. The Great Attractor region really does influence our neighbourhood, but a major underdensity on the other side appears to contribute to the same general motion. This also helps explain why simply counting visible galaxies can struggle to reproduce the entire velocity field. A dense region announces itself through abundance. An underdense region announces itself through motion. You can discover Shapley because there are many galaxies there. You may discover a giant repeller because galaxies elsewhere are moving as though something important is missing. This is one of the more interesting reversals in observational astronomy. Normally, seeing less gives you less information. Here, seeing less matter can itself be the information. The absence becomes measurable through its gravitational consequences. There's also a reason cosmic voids can become so large. Once matter begins leaving an initially underdense region, there is less material inside it to slow the process relative to its denser surroundings. The void expands relative to the background. Smaller underdense regions can merge into larger ones. matter becomes increasingly concentrated along the boundaries. Simulations show that this evacuation process helps build the sheets and filaments surrounding voids. If you could speed up billions of years of cosmic evolution and watch one of these regions develop, you would see matter gradually draining away from the interior. Galaxies near the center would move outward. Matter would collect along walls. Filaments would become more pronounced. Dense knots would form where several filaments meet. The void would occupy a larger volume while containing relatively little matter. It would look less like something actively pushing its surroundings and more like a region being emptied as gravity draws material toward denser places. That is closer to what is actually happening. Even the term void expansion requires some care. The entire universe is already expanding. A void expands in an additional sense because its interior is underdense, and the local expansion there can exceed the average expansion rate. The surrounding matter develops outward peculiar velocities relative to the background Hubble flow. Again, the word peculiar does not mean strange. It simply means extra motion beyond what the smooth cosmic expansion predicts. Those extra velocities are exactly what the cosmic flow surveys are designed to measure. This gives astronomers an unusual way to map the invisible architecture of the nearby universe. Instead of only asking, where are all the galaxies? They can ask, where would the galaxies move if this density field were correct? Then they compare that predicted flow with observations. Dense structures generate convergence. Underdense structures generate divergence. If the reconstructed velocity field repeatedly points away from the same broad region, that region becomes a candidate repeller. The Dipole Repeller was identified in precisely this kinematic sense. The 2017 research did not begin by photographing a gigantic, empty sphere and attaching the name Dipole Repeller to it. The evidence came from the velocity field. The authors found that the local group's bulk flow is closely anti-aligned with the direction of the repeller over a large range of scales. Their reconstruction placed the relevant repelling influence at a distance corresponding to roughly 16,000 kilometers per second in their velocity distance coordinate system, with a substantial uncertainty of about 4,500 kilometers per second. They predicted that this repeller should correspond to a large void in the galaxy distribution. That wording matters. Predicted to be associated with a void. The velocity reconstruction was stronger than the direct observational map of the matter distribution in that direction. This is partly because the proposed region lies far away, and partly because an underdensity is intrinsically harder to map than a rich supercluster. If Shapley contains an unusually large number of galaxies, even an incomplete survey can begin revealing the concentration. If the Dipole Repeller contains unusually few galaxies, poor survey coverage and genuine emptiness can look frustratingly similar. You have to determine whether the missing galaxies are really missing or simply have not been observed. This is one reason researchers use several kinds of data and reconstruction techniques. Redshift surveys tell us where detected galaxies lie. Distance measurements give peculiar velocities. Cosmological models connect those velocities to the underlying density field. Simulations help test whether the reconstructed structures are plausible. Later work, using more advanced reconstructions of the nearby universe, continue to recover the Dipole Repeller as a significant void-like feature, alongside major clusters and superclusters such as Virgo, Centaurus, Coma, Shapley, and Perseus Pisces. So the repeller did not vanish when researchers changed reconstruction methods. It remained part of the large-scale picture. This is reassuring because statistical reconstructions always raise the question of whether an apparent structure might be an artifact of incomplete data. If a feature repeatedly appears under different approaches and is consistent with observed peculiar velocities, confidence in its physical significance increases. Still, the word repeller can continue causing trouble if we imagine it too literally. Suppose you could travel toward the center of a cosmic void. You would not encounter a boundary where an invisible force suddenly began pushing your spacecraft backward. There would be no repulsion field for your instruments to detect. You would simply enter a region with fewer galaxies and less matter than average. Locally, gravity would continue behaving normally. The repulsion becomes meaningful when you describe the large-scale motion relative to the average density of the universe. This is similar to describing air rising in the atmosphere. You might say a warm region of air rises because it is buoyant. There is not a mysterious upward force built into warm molecules. Its motion comes from differences in density and pressure within the larger environment. The large-scale behavior emerges from an imbalance. With cosmic voids, the imbalance is gravitational. More matter over there, less matter over here. The result is a preferred flow. For the Milky Way and the local group, this is especially effective because the main repelling direction and the major attracting direction are arranged approximately opposite one another. Shapley sits broadly ahead along the large-scale motion. The Dipole Repeller lies broadly behind it. The combination resembles standing between a crowded region, pulling you from one side, and a nearly empty region, failing to provide a balancing pull from the other. You move toward the crowd and away from the emptiness. If you only looked ahead, you would say the crowd caused the motion. Once you map the whole room, you realize that the missing people behind you are part of the explanation too. This way of thinking also changes how we understand the cosmic web itself. Voids are not passive holes between the important structures. They participate in shaping those structures. Their expansion helps move matter into walls and filaments. Their gravitational imbalance contributes to peculiar velocities. Their boundaries can influence where galaxies accumulate. The crowded universe and the empty universe are therefore not separate stories. They develop together. A filament becomes dense partly because matter has been drawn toward it. A neighbouring void becomes empty partly because matter has moved away from its interior. The same redistribution produces both. That is why an enormous void can influence our motion even though it contains less mass than the region surrounding it. Its importance comes from the contrast. If the universe around us were perfectly uniform, there would be no Dipole Repeller. There would be no Shapley attractor either. There would be no large peculiar velocity caused by density variations. The fact that we are moving at hundreds of kilometers per second relative to the CMB is evidence that the universe around us is not balanced. The density field has structure. The CMB tells us the local group is moving. Galaxy velocities tell us how the surrounding matter is flowing. The reconstructed density field tells us where the major gravitational imbalances are likely to lie. On one side, the answer is comparatively easy to recognize because the sky contains a huge concentration of galaxies. On the other, the answer is defined by scarcity. The name Dipole Repeller entered the scientific literature in 2017 when Yehuda Hoffman, Daniel Pomered, R. Brent Tully, and Hélène Courtois published an analysis of the peculiar velocity field around the local group. Their result did not come from finding a strange object in a telescope image. There was no bright source sitting in the relevant direction, no newly discovered galaxy cluster, and certainly no object producing a known repulsive form of gravity. The clue came from the way galaxies were moving. When the researchers reconstructed those motions in 3 dimensions, the large-scale flow around us appeared to be organized by 2 dominant influences: attraction toward the Shapley concentration on one side, and motion away from a previously unidentified underdense region on the other. They called that underdense influence the Dipole Repeller. The word dipole is important here because it tells us something about the type of motion being studied. In a mathematical description of a velocity field, the simplest large-scale component is the bulk flow, sometimes described as the dipole moment. It represents a broad tendency for an entire region to move in one preferred direction. The local group has exactly this kind of motion relative to the cosmic microwave background, with a velocity of about 631 kilometers per second. Hoffman and his colleagues found that this bulk flow direction was closely aligned away from the repeller. In other words, if you draw an arrow showing the local group's large-scale motion, then look in approximately the opposite direction, you're looking toward the region associated with the Dipole Repeller. That is what behind us means in this context. There is no permanent cosmic behind. Space does not come with a front, a back, a ceiling, or a conveniently marked arrow saying, Milky Way travelling this way. The word only makes sense relative to the local group's measured motion. If Shapley lies broadly toward the direction in which the large-scale flow is heading, the Dipole Repeller lies broadly toward the opposite end of that motion. If you could turn around while somehow watching the local group travel through the cosmic web, the repeller would be on the side we're leaving. That does not mean we've recently passed it. The local group has not flown close to the centre of the Dipole Repeller like a spacecraft passing a planet and then continued onward. The motion developed gradually under gravity as large-scale structure evolved. The region associated with the repeller has probably been underdense for billions of years, with matter flowing away from it toward denser surroundings as the cosmic web developed. The word repeller can still make the situation sound more exotic than it is. Nothing in the 2017 result required a new fundamental force. The researchers worked within the standard cosmological picture in which structure grows from initial density variations under gravity. Overdense regions attract matter. Underdense regions produce peculiar accelerations away from themselves when their gravitational effect is considered relative to the average density of the universe. The Dipole Repeller is therefore not a source of anti-gravity. It is an extreme example of a familiar gravitational consequence of having too little matter in one enormous region. Suppose the universe around us contained exactly the average amount of matter in every direction. The pull from one side would be balanced, in the large-scale statistical sense, by matter on the other side. Now place a large concentration such as Shapley in one direction. The balance changes and we accelerate partly toward it. Next, reduce the amount of matter over a huge region on the opposite side. The balancing attraction becomes even weaker. Our acceleration toward the Shapley side becomes larger. Describe the same situation from the underdense side, and we appear to be moving away from it. That is the repeller. It is useful to think of this as a gravitational accounting problem. Shapley gives the universe an unusually large positive entry on one side of the ledger. A huge void gives it an unusually large deficit on the other. The resulting imbalance contributes to the motion we observe. The surprising result from Hoffman and his colleagues was that the underdense side did not appear to be a minor correction. Their reconstruction suggested that the Shapley-associated attractor and the Dipole Repeller made roughly comparable contributions to the CMB dipole. The large peculiar velocity of our local group was therefore not simply a story of being pulled toward a crowded region. A major part of the explanation appeared to come from the deficit of matter in the opposite direction. That changed the emphasis of the problem. For decades, the natural approach had been to ask where enough mass could be found to pull the local group at hundreds of kilometers per second. First came nearby influences, then the Great Attractor, then increasingly distant structures, including Shapley. Each discovery added mass to the attracting side. The Dipole Repeller showed why that search could remain incomplete even after astronomers became very good at cataloguing overdense structures. They had been concentrating on places where there were more galaxies. The velocity field was also sensitive to places where there were fewer. Finding a dense supercluster is relatively straightforward in principle. Point telescopes toward the region, identify large numbers of galaxies, measure their redshifts, and determine that the galaxy density is unusually high. Finding a distant void is less convenient. If a telescope survey records few galaxies in one direction, at least two explanations are immediately possible. Perhaps there genuinely are few galaxies there, or perhaps your survey simply failed to detect them. Maybe the galaxies are too faint. Maybe the observations are incomplete. Maybe galactic dust obscures part of the region. Maybe the redshift catalogue has poor coverage. An empty-looking map does not automatically prove the existence of a cosmic void. Velocity data provide another way to approach the problem. Instead of asking only how many galaxies occupy a region, researchers examine how galaxies throughout the surrounding volume are moving. If many peculiar velocity vectors systematically point away from approximately the same location, that is difficult to explain as a simple hole in the observational catalogue. Something about the large-scale gravitational field is producing divergent motion. This is what made the Dipole Repeller detectable, even though the associated matter deficit was difficult to chart directly. The 2017 analysis used galaxy peculiar velocities from cosmic flows too. Those observations provided distance information for thousands of galaxies and galaxy groups. By comparing independently measured distances with recession velocities, researchers could estimate the deviations from the smooth Hubble expansion. Those deviations are the peculiar velocities produced by the gravitational environment. There is a practical difficulty, though. For most distant galaxies, astronomers cannot simply watch an object move sideways across the sky and measure its complete three-dimensional velocity. The angular motions involved are generally far too small. What they can measure much more effectively is the radial component, the motion toward or away from us. This means the observations give an incomplete sampling of the full velocity field. There are also uncertainties in galaxy distance measurements, and those uncertainties become important because peculiar velocities are found by subtracting one large quantity from another. The researchers therefore used a statistical reconstruction method known as a Wiener filter. The name has nothing to do with sausages despite the unfortunate temptation. It is a mathematical method used to estimate an underlying signal from incomplete and noisy data. In this case, the goal was to infer the three-dimensional density and velocity fields most consistent with the measured peculiar velocities and the expected statistical properties of structure in the standard cosmological model. Once the velocity field was reconstructed, the researchers could do something that is extremely difficult with ordinary sky maps. They could follow the flow. Imagine placing thousands of tiny arrows throughout a three-dimensional model of the nearby universe. Each arrow represents the reconstructed peculiar velocity at that location. Now connect those arrows into streamlines. Near a major attractor, the streamlines bend inward and converge. Near a repeller, they spread outward. The result resembles a complicated weather map, except the arrows represent galaxies moving through structures hundreds of millions of light-years across, rather than air moving across tomorrow's forecast. When Hoffman and his colleagues followed those streamlines, the large-scale pattern revealed a clear repelling direction. The bulk flow of our region was closely anti-aligned with that repeller out to a distance coordinate of about 16,000, plus or minus 4,500 kilometers per second in the convention used in the reconstruction. That notation can look strange because kilometers per second normally describes velocity, but extragalactic astronomers often use recession velocity as a convenient proxy for distance through the Hubble relation. The important point is that this was not a small empty pocket immediately outside the local group. The inferred repelling influence existed on an enormous cosmological scale. The researchers also examined another part of the velocity field called the shear. Bulk flow tells you how an entire region is moving together. Shear tells you how that flow changes across the region. One direction may be stretching while another is compressing. This additional information gave them another way to identify the structures shaping the motion. The expansion direction of the shear field was closely connected with the Shapley attractor over substantial distances, while the bulk flow direction pointed strongly away from the Dipole Repeller. Together, those patterns supported the idea that the local group was caught between a major overdensity and a major underdensity. The arrangement is almost suspiciously convenient for anyone trying to explain it to another person. A large attractor ahead, a large repeller behind, our galactic neighbourhood moving between them. Nature does occasionally provide a diagram that looks as though someone prepared it for a presentation. The real field is more complicated than this simplified picture. There are many smaller attractors and repellers, many galaxy clusters, many voids, and many local flows superimposed on one another, but the dominant large-scale contribution could be summarized surprisingly well by those two main features. This is why the word dipole fits so neatly. At the simplest level, the velocity field looks like a flow with two opposing sides. One side is associated with excess matter, the other is associated with missing matter. We sit somewhere between them. There is another detail worth noticing. The Dipole Repeller was not exactly a surprise in the sense that nobody had ever imagined an underdensity might influence the local group. Earlier work had already suggested that a major underdense region in the northern galactic hemisphere, at a distant scale of roughly 15,000 kilometers per second, could contribute significantly to the observed flow. The 2017 work provided a more direct kinematic reconstruction and identified the repeller as a dominant feature of the local velocity field. So the breakthrough was not the invention of the idea that voids affect motion. Cosmologists already understood that. The important step was showing that a specific large underdensity could be identified dynamically, and that its contribution to our motion appeared comparable to the attraction associated with Shapley. That immediately raised another question. Was the Dipole Repeller real, or could it be an artifact of the reconstruction? This is always a concern when scientists infer something that is difficult to observe directly. A galaxy cluster can eventually be confirmed by many independent observations. You can detect its galaxies, measure its X-rays, estimate gravitational lensing, measure velocity dispersion. A repeller identified primarily through reconstructed peculiar velocities requires a different kind of confidence. One useful test is to change the reconstruction method or improve the data and see whether the structure survives. That happened. In 2018, Hoffman and colleagues published a different reconstruction technique designed to recover the quasi-linear density and velocity fields of the nearby universe, using ensembles of constrained cosmological simulations. The resulting maps robustly recovered familiar structures such as the Virgo, Centaurus and Coma clusters, the Shapley and Perseus-Pisces superclusters, and the Dipole Repeller among the major void-like structures. That was important because the new approach was not simply drawing the same velocity arrows again. The team generated cosmological simulations constrained by observational peculiar velocities, then examined the matter distributions compatible with those data. If a supposed feature appears only because one mathematical reconstruction method behaves badly in a poorly sampled region, it may disappear when the analysis changes. The Dipole Repeller remained. The exact shape, center, size, and boundaries of a large void are naturally less sharply defined than the surface of a planet or star. Cosmic structures overlap and merge. Their properties depend partly on the smoothing scale used in the analysis. Still, repeated recovery of the broad underdensity strengthens the case that the repelling feature corresponds to a genuine part of the large-scale matter distribution. Cosmic Flows 3 provided yet another perspective. Using a larger compilation of galaxy distances, researchers modelled the gravitational velocity field within a much broader nearby volume. That reconstruction again recovered the dipole repeller near the anti-apex of the CMB dipole. It also revealed another major basin of repulsion in a different direction, toward the region of the famous CMB cold spot. That result helps correct another possible misunderstanding. The Dipole Repeller is not the only repeller in the universe. There is no reason it should be. The cosmic web contains many voids. Each underdensity can contribute to local peculiar velocities. What makes the Dipole Repeller special is its relationship to us. It lies in the direction strongly associated with the local group's peculiar motion and with the dipole component of the surrounding velocity field. If we lived in a different galaxy hundreds of millions of light years away, another underdensity might play the same role in our local motion. The name is therefore somewhat Earth-centered, or more accurately local group-centered. The universe itself has not marked this particular void as special. We have, because it helps explain why we're moving the way we are. This also tells us something useful about what astronomers mean when they speak of our local universe. In normal conversation, local might mean the next street, or perhaps the nearest supermarket. In cosmology, researchers can use local while discussing structures extending across hundreds of millions of light years. The scale changes because the universe is very large, and the cosmic web operates across enormous distances. The Milky Way is one galaxy among a vast number. The local group contains our nearest large galactic companions. Beyond that are clusters, filaments, superclusters, and voids. The Dipole Repeller belongs to that much larger environment. Its effect on us is therefore not like the gravitational influence of a nearby object. You could not point a conventional telescope toward it and expect to see one thing responsible for the motion. The effect comes from the density field across a huge volume. This is where dark matter also becomes part of the story. Galaxy surveys show us luminous matter, but galaxies do not contain all of the mass. Most of the gravitating matter associated with large-scale structure is dark matter. Peculiar velocity reconstructions respond to total gravitational mass, whether it shines or not. That is one reason velocity fields are so valuable. Galaxies behave like tracers moving through a gravitational landscape shaped by both visible and dark matter. The 2018 quasi-linear reconstruction specifically emphasized that peculiar velocities provide information about the underlying matter field and robustly recovered both overdense and underdense structures from those motions. A void, therefore, means a deficit in the total matter field, not merely an area where stars forgot to form. There may be fewer galaxies because less matter accumulated there in the first place. There is also less dark matter than average. That combined underdensity produces the gravitational imbalance. If you were transported into such a region, you might still see galaxies in the distance. You might even find occasional galaxies within the void itself. But compared with a dense filament or supercluster, the surroundings would be remarkably sparse. There would be fewer large gravitational structures in every nearby direction. From the outside, matter would have been draining away from the interior for billions of years. The result is the divergent flow that allowed researchers to infer the repeller. The expression, "something is pushing the Milky Way," is therefore useful for getting our attention, but the more accurate statement is slightly different. The Milky Way and the rest of the local group are moving through a gravitational field produced by an extremely uneven cosmic matter distribution. A major concentration of matter towards Shapley contributes attraction in one direction. A major deficit of matter in the opposite direction contributes an effective repulsion when the peculiar gravitational field is described relative to the cosmic mean. Add those influences to the smaller contributions from nearby clusters, filaments, and voids, and the large CMB relative motion of our neighbourhood begins to make sense. It is tempting to ask whether the Milky Way is getting farther from the Dipole Repeller every second. In the broad peculiar flow sense, yes, our motion is directed away from the repelling region. But the full answer has to include cosmic expansion and the fact that the structures themselves participate in an evolving universe. We are not travelling across a fixed map. The map is changing while everything moves. Voids continue evolving. Dense structures continue attracting matter. On sufficiently large scales, cosmic expansion increases the separations between unbound regions. The reconstructed velocity field isolates the additional motion associated with gravitational structure from that broader expansion. This distinction is exactly why the measurements are difficult. Astronomers cannot simply look at a galaxy's recession speed and say, that is the Dipole Repeller pushing it. They first need the galaxy's distance. They need an assumed background expansion. They need to estimate its peculiar velocity. They need many such measurements across the sky. Then they need to reconstruct a three-dimensional field from incomplete radial data. Only after all of that do the attractors and repellers emerge. That flow could not be photographed in the ordinary sense. A telescope can show us a galaxy, a cluster, or a filament because those structures contain luminous objects. It cannot take a normal picture of a peculiar velocity. Motion on these scales has to be extracted from measurements, and the useful information is often hidden inside numbers that initially seem to describe something else. The first number astronomers need is a galaxy's redshift. When light travels through an expanding universe, its wavelength is stretched. Spectral features that would appear at familiar wavelengths in a laboratory shift toward longer, redder wavelengths. By measuring that shift, astronomers obtain an extremely precise indication of how rapidly a distant galaxy is receding along our line of sight. For a sufficiently nearby galaxy, however, that observed recession is not produced by cosmic expansion alone. The galaxy also has its own peculiar velocity caused by the gravitational influence of surrounding matter. A galaxy might be moving slightly toward us relative to the smooth expansion. Another might be moving away faster than the average expansion predicts. A whole collection of galaxies might share a coherent additional movement toward the same massive structure. The redshift contains all of those effects mixed together. To separate them, astronomers need a second measurement that is much harder to obtain, the galaxy's actual distance. That might seem slightly backwards. You could reasonably assume that if astronomers already know a galaxy's redshift, they already know its distance. Redshift is indeed commonly used to estimate distance, but doing that assumes the galaxy is following the average expansion reasonably well. If your purpose is to discover departures from that average expansion, using redshift alone would erase much of the information you're trying to find. The researchers therefore need distance measurements that do not depend primarily on the galaxy's recession velocity. Once they have such a distance, they can estimate how fast cosmic expansion should be carrying that galaxy away. They then compare the expected recession with the observed recession. The difference provides the galaxy's peculiar velocity along our line of sight. This basic relationship is central to the way peculiar velocity surveys map the local universe. The same principle was used in the cosmic flows work and in the velocity-based definition of Laniakea. Measure distance directly, calculate the expansion expected at that distance, and subtract it from the observed motion. The arithmetic sounds much easier than the observations. Astronomers cannot stretch a tape measure from Earth to another galaxy. They need objects or relationships whose intrinsic properties allow distance to be inferred. Some nearby galaxies contain Cepheid variable stars. Cepheids brighten and dim with periods related to their intrinsic luminosities. Measure the period, estimate how luminous the star really is, compare that with how faint it appears from Earth, and distance can be calculated. Another technique uses the tip of the red giant branch. Old low-mass stars reach a characteristic luminosity near the end of a particular stage of stellar evolution. If astronomers can resolve the stars in a nearby galaxy well enough, that feature provides another distance indicator. Surface brightness fluctuations provide yet another method. A galaxy may look like a smooth patch of light from a distance, but its image contains tiny statistical variations produced by the finite number of stars contributing to each resolution element. The apparent strength of those fluctuations changes with distance. Type 1. A supernovae can be seen vastly farther away and can be standardized well enough to provide particularly valuable distance measurements. Then there are relationships involving entire galaxies. Spiral galaxies show a correlation between luminosity and rotational speed, commonly used through the Tully-Fisher relation. Elliptical galaxies and related systems can be measured using relationships among quantities such as their size, surface brightness, and internal stellar velocities, usually summarized through the fundamental plane. Cosmic flows, too, combined all of these approaches onto a common distance scale rather than relying on one technique alone. This combination was necessary because every method has limitations. Cepheids are excellent but difficult to measure in very distant galaxies. The tip of the red giant branch is highly useful where individual stars can be resolved, but eventually becomes observationally impractical. Type 1. A supernovae are bright enough to be seen across much greater distances, but nature does not arrange one in every galaxy precisely when an astronomer needs a distance measurement. Galaxy scaling relations can provide measurements for much larger samples, but their individual distance uncertainties are generally larger. The solution is to combine overlapping methods. Accurate nearby indicators help establish the scale. Other methods extend that scale farther outward. Galaxy groups can help because several galaxies may share approximately the same physical distance even when their individual measurements are noisy. Slowly, the distance ladder reaches into the volume where the large-scale cosmic flow becomes visible. Cosmic flows, too, was particularly important in the Dipole Repeller analysis because it assembled distances and peculiar velocities for more than 8,000 galaxies. More than 1,000 of its distance estimates came from relatively precise techniques, such as Cepheids, the tip of the red giant branch, surface brightness fluctuations, Type 1a supernovae, and other high-quality procedures, while much of the larger sample came from the Tully-Fisher and fundamental plane relations. The survey was densest and most accurate nearby, and became progressively sparser at larger distances, extending to roughly redshift 0.1. 8,000 galaxies sound like an enormous number until you compare them with the volume being mapped. The observable universe contains galaxies in almost every direction. The cosmic flows measurements were scattered irregularly through a three-dimensional region. Some parts were sampled well, others had relatively few usable distance measurements. The uncertainties were also not identical from one object to another. And there was another limitation. Astronomers mainly measure radial peculiar velocity. That means the component directed toward us or away from us. Imagine watching cars from a tall building. If a car drives directly toward the building, you can easily see its distance changing. If another travels sideways across your field of view at the same distance, determining its true speed from that change in distance would be impossible. Galaxies create a similar problem on a much greater scale. Their sideways motion across the sky is generally far too small to measure directly for the purpose of mapping these large-scale flows. The most accessible velocity information comes from the line-of-sight component, so astronomers had thousands of measurements, but most were only one component of a three-dimensional velocity vector. They needed to reconstruct the rest. That is where the mathematics became essential. The Dipole Repeller team used a Wiener filter reconstruction. A Wiener filter is a statistical method for recovering an underlying signal when the available data are noisy, incomplete, and irregularly sampled. In this application, the measured peculiar velocities were combined with the statistical expectations of the standard cosmological model to estimate the most likely three-dimensional velocity and density fields. The method had already been developed and applied to peculiar velocity reconstruction before the Dipole Repeller work. You can think of the problem as trying to understand a wind field using weather stations scattered across a country. Suppose each station tells you only whether the wind is moving somewhat toward or away from your own location. Some stations are missing, some measurements contain large uncertainties. You still know that real winds tend to form smooth, physically related patterns rather than changing randomly every few meters. A reconstruction method uses that combination of observations and expected physical behavior to infer the most probable larger flow. It does not invent whatever pattern looks visually pleasing. It calculates the field that best fits the measurements, while remaining statistically consistent with the cosmological model used in the analysis. Where the data are strong, observations exert more influence. Where the data becomes sparse, the reconstruction becomes less certain and tends toward the statistical mean expected by the model. That point matters because reconstructed cosmic maps are not equivalent to direct photographs. They come with uncertainty. A feature well constrained by nearby measurements is more secure than a distant feature appearing in an area with poor coverage. Scientists therefore examine not only the reconstructed field, but also how robust its features are when assumptions, data samples, or reconstruction techniques change. The original Dipole Repeller analysis used the peculiar velocity reconstruction to identify where the flow converged and diverged. Its principal result was that the local group's large-scale motion could be described by a dominant attractor associated with Shapley and a previously unidentified repeller associated with an underdense region. The two were found to contribute roughly equally to the observed CMB dipole, with the local group's bulk flow remaining closely anti-aligned with the repeller out to a distance coordinate of about 16,000 plus or minus 4,500 kilometers per second. The researchers did not need to see the void clearly first. The galaxies told them it should be there. Their motions provided the clue. This is the unusual advantage of peculiar velocities. Light surveys trace luminous matter, and galaxies themselves are biased traces of the full matter distribution, because the relationship between where galaxies form and where all matter exists is not perfectly simple. Peculiar velocities respond to the gravitational field generated by total matter, including dark matter. Later constrained reconstructions using cosmic flows 2 emphasize precisely this advantage and robustly recovered familiar structures such as Virgo, Centaurus, Coma, Shapley, Perseus Pisces, and the Dipole Repeller in the underlying matter field. That makes galaxy motion a little like observing the movement of iron filings without being able to see the magnet. You may not know immediately what is creating the field, but the pattern of motion contains information about it. A dense concentration of dark matter can influence galaxies whether or not the dark matter itself emits a single photon. An underdense region can influence the flow, even though its defining feature is a shortage of objects to observe. Gravity reveals both. There is another obstacle hidden inside the distance measurements themselves. Errors in distance are not always harmless random fuzz. They can systematically distort reconstructed peculiar velocities. Suppose a galaxy's true distance is slightly overestimated. You then calculate that cosmic expansion should be carrying it away faster than it actually should. When you subtract that expected expansion from the observed recession velocity, you can create an artificial peculiar velocity toward us, underestimate the distance, and the error goes the other way. Because galaxy samples are not distributed uniformly, and because distance uncertainties behave in specific statistical ways, these effects can generate biases if they are not treated carefully. One famous example is Malmquist bias, a family of selection effects that can arise because brighter objects are easier to observe over larger volumes and because distance errors interact with an uneven distribution of galaxies. These issues become increasingly troublesome as surveys reach farther and individual distance errors grow. That is why later cosmic flows analyses did not simply accept every measured distance as an exact coordinate and subtract a Hubble flow value from it. More advanced approaches treated distances, peculiar velocities, calibration uncertainties, and the underlying density field together statistically. A 2019 analysis of cosmic flows 3 used hierarchical Bayesian forward modelling to infer the peculiar velocity and matter density fields out to about redshift 0.054. The authors explicitly designed the method to mitigate problems including homogeneous Malmquist bias and the non-Gaussian behaviour that arises when distance errors are converted into peculiar velocities. Their recovered velocity field had location-dependent statistical uncertainties of roughly 150 km per second and covered a volume about 10 times larger than previous comparable reconstructions. Cosmic Flows 3 was itself a major expansion of the observational effort. The broader idea remained the same: gather direct galaxy distance estimates, combine them onto a consistent scale, compare distance with redshift, infer peculiar motion, then allow the velocity information to constrain the matter distribution that could have produced it. Each generation improved the sampling and the statistical treatment. There is a nice reversal hidden inside that procedure. Normally, we think matter determines motion. Here, astronomers observe motion and use it to determine matter. The laws of gravity provide the connection in between. If several neighbouring galaxies have peculiar velocities aimed toward the same region, the reconstruction expects additional matter there. If the flow spreads away from a region, the reconstruction expects an underdensity. When many such constraints are combined, a 3-dimensional map appears. The result can then be visualized using streamlines. A streamline is not the literal path that one particular galaxy has followed since the beginning of time. It is a representation of the direction of the reconstructed velocity field at each location. Place a starting point into that field and trace the local velocity direction forward, and the line shows where the flow leads. Near an attractor, many lines converge. Around a repeller, they diverge. Daniel Permerade and colleagues used sophisticated three-dimensional visualization to make these velocity fields easier to interpret, allowing researchers to rotate the reconstructed volume, examine slices through it, and watch how streamlines connect the major structures. The Dipole Repeller paper included both sliced views and a three-dimensional representation of this flow. These visualizations helped make something abstract unusually clear. The local group was not sitting at the center of a set of random arrows. It belonged to an organized flow. Trace that flow one way, and it leads broadly toward the Shapley side. Trace it backward, and it diverges from the dipole repeller side. Nearby structures bend the streamlines. Virgo modifies the local flow. Other clusters and voids leave their own signatures, yet the large-scale pattern survives beneath those smaller deviations. The same general technique had already produced another major change in how our cosmic neighborhood was described. In 2014, Tully, Courtois, Hoffman and Pomerade used peculiar velocities to define the Laniakea supercluster. Rather than trying to decide where one supercluster ended by looking only at galaxy concentrations, they examined the velocity field and identified a basin of attraction. Galaxies within that region showed flows that converged toward a common gravitational basin after the background expansion was accounted for. The boundary could then be defined by separating streamlines that drained into different basins. The analogy is much like mapping watersheds on Earth. Rain falling on one side of a mountain ridge eventually reaches one river system. Rain falling a short distance away on the opposite side reaches another. The ridge defines a boundary even though there is no painted line on the ground. Peculiar velocity basins allow cosmologists to draw similar boundaries through the cosmic web. The Milky Way belongs to one flow basin locally. At still larger scales, that entire region participates in another bulk motion. This is why maps of cosmic structure depend partly on the scale at which you examine them. Stand beside a small stream and the nearest bend determines where the water moves. Zoom out and the stream belongs to a river. Zoom farther and the river belongs to a drainage basin. The local direction remains real, but it sits inside progressively larger systems. Galactic motion works in much the same way. The Milky Way responds to the local group. The local group responds to surrounding clusters and voids. Our larger region participates in a bulk flow extending much farther. Cosmic flows allows researchers to separate these layers. Still, a statistical reconstruction is only as convincing as its ability to survive independent tests. That is why the 2018 work on the quasi-linear nearby universe was valuable. Instead of relying on a single, smoothed linear reconstruction, Hoffman and collaborators generated an ensemble of constrained cosmological simulations, consistent with the observed peculiar velocities and the standard cosmological model. From those simulations, they reconstructed the quasi-linear matter and velocity fields, including some of the non-linear structure that simpler methods smooth away. The major nearby clusters, superclusters, and the Dipole Repeller were recovered robustly across the ensemble. Constrained simulation deserves a moment because it is an unusual kind of simulation. Many cosmological simulations begin with statistically plausible initial conditions and allow gravity to evolve them. The resulting universe may look statistically like ours while containing completely different individual structures. There may be galaxy clusters, there may be voids, there may be filaments, but there is no requirement that a simulated Virgo cluster appear where our actual Virgo cluster is located. A constrained simulation does something more specific. Observational data are used to restrict the initial conditions so that, when the simulated universe evolves, its large-scale environment resembles the one we actually observe. Peculiar velocities are particularly valuable constraints because they respond to the total gravitational field and preserve information about structures over relatively large scales. Earlier work developing these simulations showed how Wiener filter reconstructions of radial peculiar velocities could be combined with techniques that estimate earlier positions and generate constrained initial conditions for simulations of the local universe, researchers can then run multiple versions. The small-scale details differ because the data cannot determine every galaxy and every dark matter halo exactly. But large structures repeatedly required by the observations should reappear. If Virgo forms in roughly the correct region across many realizations, that tells you the constraints are strongly demanding something like Virgo. If a major underdensity repeatedly develops near the Dipole Repeller location, confidence increases that the feature is not simply a quirk of one map. This combination of observation, reconstruction, and simulation is how astronomers find things that cannot be detected by one straightforward photograph. No single measurement reveals the entire cosmic flow. A redshift provides one clue, a distance provides another. Thousands of galaxies reveal coherent peculiar velocities. Statistics fill the gaps while keeping track of uncertainty. Gravity connects velocity to density. Simulations test whether the inferred structures can arise naturally in a universe governed by the same cosmological rules. Visualization finally turns the result into something a human brain can inspect without spending the evening staring at a matrix of numbers. And through all of that, the apparently invisible region behind our motion becomes visible indirectly. Not because it shines, because everything around it moves. The same logic applies to Shapley from the opposite side. There, the abundance of galaxies gives direct evidence for an overdensity, while the converging velocity field provides dynamical evidence that the excess matter affects its surroundings. For the Dipole Repeller, the visual evidence is weaker precisely because there is less to see. The divergent flow becomes particularly important. The two sides therefore complement one another. One announces itself through excess, the other through deficit. The galaxy velocities respond to both. This is also why the motion of our local group cannot be reconstructed simply by drawing a straight line between the Milky Way and Shapley. The velocity field contains curves. Nearby structures redirect portions of the flow. Smaller voids provide additional divergence. Clusters provide additional convergence. Different scales reveal different dominant features. Yet after these local complications are included, the broad motion still has a remarkably understandable geometry. Our neighbourhood sits in an uneven matter distribution. There is substantially more gravitational attraction along one broad side. There is substantially less on another. The CMB gives us the final velocity vector produced by that imbalance. Peculiar velocity measurements allow astronomers to work backward from the motion and recover much of the gravitational landscape responsible. So when someone says scientists discovered the Dipole Repeller, the word discovered has a slightly unusual meaning. They did not point a telescope at one coordinate and see an object. They measured thousands of other objects. They determined how far away those galaxies were. They compared those distances with their redshifts. They extracted small departures from the general cosmic expansion. They reconstructed a velocity field. They traced its streamlines. They found a region from which the large-scale flow diverged. Then independent reconstruction methods and constrained simulations continued to recover an underdense feature in the same broad part of the surrounding cosmic web. The invisible structure revealed itself through the behavior of everything else. With that map in hand, the original question about the Milky Way changes again. We no longer have to choose between saying that Shapley pulls us or that the Dipole Repeller pushes us. Both descriptions point to parts of the same gravitational imbalance. The useful question, then, is not whether the Milky Way is being pulled or pushed. It is how an uneven universe can produce a motion that can be described from both directions at once. If we could remove the distracting glow of individual stars and replace the nearby universe with a map showing only its gravitational landscape, the picture would not be uniform. Dense regions would occupy some parts of the map. Underdense regions would occupy others. The local group would sit inside that uneven distribution, responding to the combined influence of the matter around it. That is the situation in which the Milky Way finds itself. On one broad side lies the Shapley concentration, one of the major overdense structures affecting the large-scale flow around us. On roughly the opposite side lies the underdense region identified through the Dipole Repeller reconstruction. Between those two extremes are the Great Attractor region, Virgo, nearby voids, filaments, smaller clusters, and many other structures that contribute to the velocity field. The local group does not choose between those influences. Gravity adds them together. The 2017 reconstruction found that our local group moves at about 631 plus or minus 20 kilometers per second relative to the cosmic microwave background, and identified a dominant attracting influence associated with Shapley and a major repelling influence in nearly the opposite direction. It becomes easier to understand if we return to the example of ropes, but make it a little more realistic. Imagine you are sitting in a chair with ropes attached from many directions. Some ropes are pulled by large groups of people, others are pulled by only one or two. In a few directions there are hardly any people pulling at all. Your movement is determined by the combined effect of every rope. Now put a very large group on your right. Their pull becomes significant. On your left, leave a large section almost empty. There is much less pull balancing the force from the right. You begin moving to the right. Nobody on the left has pushed you. The imbalance in attraction is enough. Translate that into the cosmic web, and the general idea becomes clearer. Shapley represents a region containing much more matter than average. The Dipole Repeller corresponds to a region containing much less matter than average. The excess on one side and the deficit on the other both favour motion in approximately the same direction. If we concentrate only on Shapley, we can say that matter ahead is pulling us. If we concentrate only on the underdense region, we can say that we are moving away from it. The complete description is that the surrounding gravitational field is unbalanced. This is why the word push needs quotation marks whenever we use it seriously. The Dipole Repeller is not producing a second kind of gravity that competes with ordinary attraction. There is no evidence for an anti-gravitational object sitting beyond our galaxy. An underdensity acts as a repeller in the peculiar gravitational field because it contains less matter than the cosmic mean. Matter around it experiences stronger attraction toward denser surroundings, and the resulting velocity field diverges from the void. Hoffman and his colleagues emphasize that underdense regions can be dynamically as important as overdense ones, even though they are much more difficult to chart because they contain relatively little light. The especially interesting part of their result was that the underdense side did not appear to be a minor adjustment to a story dominated entirely by Shapley. In the reconstructed flow, the Dipole Repeller and the Shapley-associated attraction were both major contributors to the CMB dipole. That does not mean every possible reconstruction will assign exactly half the motion to one and half to the other. The numerical contribution of an individual structure depends on the data, the volume included, the smoothing scale, and the way the velocity field is decomposed. There are many overlapping gravitational influences, and nature has not placed a small label beside each supercluster saying exactly how many kilometers per second it contributes. What matters is the broader result. Our motion is not adequately described as a simple fall toward one object. It belongs to a flow, and that word is useful because neighbouring galaxies share parts of the same motion. We're not watching one isolated galaxy race across an otherwise stationary universe. Entire regions participate in coherent peculiar velocities because they occupy the same gravitational environment. The flows can be followed in reconstructed maps much as meteorologists follow large patterns of moving air, although the scale here is hundreds of millions of light years, and the moving objects include entire groups of galaxies. This is where Laniakea helps us separate one level of motion from another. In 2014, R. Brent Tully and colleagues used galaxy peculiar velocities to define our home supercluster as a basin of attraction, rather than simply drawing a boundary around a concentration of visible galaxies. They measured where peculiar velocity flows diverged, traced a boundary around the region whose internal motions converged after the mean cosmic expansion, and larger scale flows were removed, and named that region Laniakea. It stretches roughly 160 megaparsecs across, and includes structures such as Virgo, Norma, Hydra, Centaurus, the Pavo-Indus filament, and a number of voids. That gives us one level of the current. Inside Laniakea, galaxies respond to the gravitational geography of the region. Virgo influences the nearby flow. The Hydra, Centaurus, and Great Attractor area becomes important farther out. Filaments redirect matter toward dense nodes. Voids contribute outward peculiar velocities. Our local group belongs to that network. But Laniakea does not sit motionless once we draw a boundary around it. The local flow can be separated mathematically from a larger bulk motion, and that broader movement is where Shapley and the Dipole Repeller become especially important. A river system provides a useful comparison. A small stream follows the slope immediately around it. It joins a larger river whose course is controlled by a wider valley. That entire river system belongs to a still larger drainage basin. If you stand beside the stream, the nearest slope explains why the water moves past your feet in one direction. If you examine a regional map, the larger terrain explains where the whole system is going. Both descriptions are correct because they refer to different scales. The Milky Way participates in a similar hierarchy. It moves within the local group. The Milky Way and Andromeda have their own relative motion. The local group participates in flows inside our wider neighbourhood. The Laniakea region has a larger motion relative to more distant structure. All of this occurs while the overall universe expands. Those motions happen simultaneously, rather than waiting politely for one another to finish. This explains why discussions of our cosmic motion can appear to give several different answers. One description emphasizes Virgo, another emphasizes the Great Attractor, another points towards Shapley, another discusses the local void. Then the Dipole Repeller enters from the opposite direction. These do not have to be rival explanations. They can be contributions on different scales. Zoom in and one set of structures dominates the map. Zoom farther out and another set becomes more important. The nearby local void provides a particularly good example. It is not the same thing as the much more distant Dipole Repeller. The local void is part of our immediate large-scale environment and has its own measurable dynamical influence. Work using Cosmic Flows 3 reconstructed the local void and estimated that its underdensity contributes roughly 200 to 250 kilometers per second to the deviant motion of the local group. That analysis found that the combination of motion away from the local void and attraction toward Virgo accounts for about half of the local group's CMB frame motion in that particular decomposition. That does not mean the remaining velocity can simply be handed to Shapley and entered into a tidy spreadsheet. The components overlap, and changing the scale at which the flow is examined changes which features stand out. What the local void demonstrates is that underdense regions are not merely empty background spaces between the structures doing the important work. They participate in cosmic dynamics. A relatively nearby void affects our local movement, while the much larger Dipole Repeller appears in the broader flow that is relevant to the CMB dipole. Thinking in terms of a current also helps explain why galaxies can have apparently contradictory motions. Leaves floating on a river can move relative to one another while being carried downstream together. One leaf can circle another in an eddy. Two leaves can approach. One can drift toward the bank. Yet all of them may still share the river's larger motion. The Milky Way and Andromeda are approaching one another because of their mutual gravitational relationship inside the local group. At the same time, both participate in much of the local group's large-scale peculiar motion. There's nothing contradictory about that. Two passengers can walk toward each other inside a moving train while both continue travelling rapidly relative to the ground. Put the train on a rotating Earth orbiting the Sun, and the comparison begins to acquire the unnecessarily complicated character of real astronomy. The same principle applies to the reconstructed cosmic velocity field. The CMB provides one particularly useful reference. Against that frame, our local group has its substantial peculiar velocity. The surrounding gravitational field helps explain why. Yet the flow is not a perfectly straight arrow from the Dipole Repeller through the Milky Way and on toward Shapley. Nearby, structures bend it, clusters create convergence, voids create divergence, filaments guide matter along preferred directions. The actual velocity field is three-dimensional and curved. This is why visualizations made from peculiar velocity reconstructions can look more like weather maps than like simple diagrams of one object falling toward another. Streamlines bend as they cross the reconstructed volume. Some gather toward attractors, others separate near repellers. Boundaries appear where flows divide and head toward different basins. The 2014 Laniakea work used precisely this type of flow behavior to define the boundary of our home supercluster. Galaxy is inside the relevant surface shared inward peculiar motions after larger components were removed, while flows outside belong to different basins. All of this gravitational geography developed gradually. The tiny density variations visible in the cosmic microwave background were far smaller than the differences between today's galaxy clusters and voids. Gravity had billions of years to amplify them. Slightly overdense regions accumulated additional matter. Galaxies formed, clusters assembled. Filaments became more pronounced. Slightly underdense regions lost matter relative to their surroundings and developed into voids. By the present era, those small beginnings have become a cosmic web with enough gravitational contrast to produce large peculiar motions. Our velocity is therefore partly a record of that history. The local group did not acquire its present motion in one dramatic event. Shapley did not suddenly switch on and begin pulling the Milky Way. The Dipole Repeller did not activate and send us in the opposite direction. The density field evolved gradually, and so did the velocity field. As mass accumulated in some places and became increasingly scarce in others, the gravitational potential changed and galaxies responded. That current should not be confused with a permanent route through a fixed landscape. The universe continues changing. Galaxies merge, clusters evolve. Matter continues moving out of underdense regions and toward denser structures, where gravity can overcome expansion. At the same time, the large-scale expansion continues. A present-day peculiar velocity streamline is therefore not the cosmic equivalent of a railway track showing exactly where the Milky Way must be in 100 billion years. Laniakea illustrates the difference between a flow basin and a single gravitationally bound object. The 2014 definition identifies a large region whose peculiar velocities converge when the average expansion and external flows are removed. It does not mean every galaxy inside that immense volume is guaranteed eventually to collapse into one gigantic cluster. The supercluster describes our present large-scale organization and flow. That same caution applies when we talk about the Shapley side of the motion. Shapley is not simply a destination waiting at the end of our journey. Saying that the local group has a peculiar velocity in its direction tells us about the present gravitational influence of the surrounding mass distribution. It does not mean the Milky Way is scheduled to arrive there after enough time has passed, nor is the Dipole Repeller a wall behind us that we have escaped. It is better to think of both as parts of the present gravitational terrain. The CMB dipole tells us the velocity produced by that terrain. Galaxy distance measurements allow researchers to infer the peculiar motions inside it. Reconstructions reveal where the flow converges and diverges. That gives us a way to identify the strongest large-scale density contrasts affecting our neighbourhood. Later work using Cosmic Flows 3 preserved the same broad picture. A reconstruction extending through a larger volume identified a major basin of attraction associated with an extension of the Shapley concentration, and again placed the dipole repeller near the anti-apex of the CMB dipole. The same analysis also found another major repelling basin in the broad direction of the CMB cold spot, reminding us that the Dipole Repeller is not the universe's only underdense structure capable of shaping a velocity field. This is an important correction to the idea that we have discovered one special void that happens to push galaxies. The universe contains many voids. It should therefore contain many regions whose peculiar velocity fields show repelling behavior. The Dipole Repeller is special to our story because of its position relative to the local group's motion. Another observer in another distant part of the universe would have a different local arrangement of attractors and repellers. The 2018 quasi-linear reconstruction strengthened this picture in another way. Researchers used an ensemble of cosmological simulations, constrained by cosmic flows to peculiar velocities, to reconstruct the underlying density and velocity fields. The method robustly recovered familiar clusters including Virgo, Centaurus and Coma, superclusters including Shapley and Perseus Pisces, and void structures including the Dipole Repeller. Because galaxy velocities respond to the total gravitational field, the method could recover information about the matter distribution beyond what a simple catalogue of luminous galaxies provides. This matters because galaxies themselves are not perfect traces of all the matter in the universe. Dark matter provides much of the gravitating mass, and the relationship between luminous galaxies and the underlying matter field is not perfectly straightforward. A dense collection of bright galaxies gives us an obvious sign that an overdensity exists. An underdensity is harder to recognize because its main observational feature is the absence of objects. Peculiar velocities give both sides a chance to reveal themselves through gravity. The result is a more balanced map. Instead of treating the bright structures as the entire story, astronomers can reconstruct the gravitational landscape from the behavior of galaxies moving through it. Shapley appears because matter is abundant and the flow converges toward the overdense side. The Dipole Repeller appears because matter is deficient and the broad velocity field diverges from its direction. This makes Shapley and the Dipole Repeller less like two unrelated cosmic opponents and more like two outcomes of the same process. One region accumulated more matter than average, the other was depleted relative to the mean. Gravity helped both contrasts grow. The overdensity became increasingly important as an attractor. The underdensity developed an outward peculiar flow as material migrated toward denser surroundings. Our local group happens to occupy a part of the larger field where those two effects reinforce one another particularly well. If the major overdensity and major underdensity were positioned in unrelated directions, their contributions could partly cancel or redirect the motion. Instead, the main repelling direction lies broadly opposite the attracting one. Moving away from the repeller also means moving broadly toward the attractor. The push and pull are therefore not fighting, they cooperate. That is the slightly counterintuitive point at the centre of the whole subject. One side contains extra matter and pulls us toward it. The other contains too little matter to provide an equivalent opposing attraction. Both conditions contribute to the same preferred direction of motion. If we return to our chair and ropes one last time, nothing mysterious needs to be added. There are many ropes. A large group pulls from ahead. Behind you, the matching group that might have balanced them is mostly absent. Smaller groups pull from the sides. The chair moves according to the total. You can spend years identifying the largest crowd ahead and still miss part of the explanation if you never turn around and notice how empty the other side is. That is essentially what happened in the history of the local group's motion. Attention first went toward the visible concentrations. Virgo mattered. The Great Attractor mattered. Shapley mattered. Better maps of the velocity field eventually made it possible to recognize that underdense regions belonged in the same calculation. The fact that astronomers can reconstruct all of this from Earth is remarkable in a very practical sense. We cannot travel to Shapley. We cannot put instruments across the interior of the Dipole Repeller. We cannot sit outside the local group and watch it move for several billion years. Instead, we receive light from galaxies. We measure their redshifts. We estimate their distances. We calculate the deviations from the smooth Hubble expansion. Thousands of those measurements are combined statistically, and gravity turns the resulting motions into information about structures we cannot directly see. From inside one galaxy, we can determine that our entire galactic neighbourhood participates in a current extending across an enormous portion of the nearby universe. That also changes what we mean by our cosmic address. Normally an address tells you where something is. We can say that Earth lies in the solar system lies in the Milky Way. The Milky Way belongs to the local group, and our wider neighbourhood sits within the Laniakea region of the cosmic web. But location is only half of the description. Our neighbourhood has motion as well. It has a velocity relative to the cosmic microwave background. It sits between large density contrasts. Nearby structures alter its path. A major underdense direction lies behind the broad flow, while a major overdensity lies ahead of it. The Milky Way is not simply located in the cosmic web, it is travelling with it, and knowing the current still leaves one question unanswered. A velocity tells us how we are moving now, but it does not automatically tell us where that motion leads. The Great Attractor is not necessarily our final destination. Shapley is not the last stop. The Dipole Repeller is not something we will simply leave farther and farther behind according to a fixed map. Our local group is evolving, the cosmic web is evolving, and the expansion of the universe is changing the relationship between structures that are not gravitationally bound. So the next question is not what is moving the Milky Way. We now have a much better idea of that. The question is where all of these motions, from our future interaction with Andromeda to the larger flow through the cosmic web, are actually taking us. The answer turns out to depend on what we mean by where the Milky Way is going. If we mean where it will be tomorrow, the answer is easy enough. It will continue moving with the local group, carrying the Sun, Earth, and everything else in our galaxy through the same large-scale gravitational flow we've been following. Its velocity relative to the cosmic microwave background will not suddenly disappear. Shapley will continue contributing to the gravitational field on one side. Underdense regions will continue affecting the balance on the other, and nearby structures will continue adding their own smaller motions. If we mean where the Milky Way will eventually arrive, however, the question becomes much more difficult. There may not be one final destination at all. The familiar picture of the Milky Way racing toward the Great Attractor can make it sound as though our galaxy is travelling to a particular place, much like a train moving toward a station. That is not really how cosmic motion works. The local group is not following a fixed track through a stationary map. The structures around us are moving as well. The universe is expanding. Galaxy groups interact. Voids evolve. Clusters gather matter. Different gravitational influences become more or less important depending on the distance and timescale being considered. Even the direction in which a reconstructed velocity streamline appears to lead depends partly on how finely astronomers smooth the cosmic velocity field. A particularly interesting study released in 2026 used digital reconstructions of the nearby universe to revisit this exact question. The researchers separated three ideas that are often treated as though they were the same. What produces the local group's present velocity relative to the cosmic microwave background, where present-day velocity streamlines appear to converge, and where the local group will actually end up in the far future. They found that these questions do not have one common answer. Depending on the scale at which the present velocity field is examined, apparent convergence shifts from Virgo on smaller scales, through the Hydra Centaurus region on intermediate scales, and towards Shapley on larger scales. No single Great Attractor-like structure dominates the entire velocity budget. That is a useful correction to the simple picture we began with. Imagine following a river using three maps. One map shows only your immediate surroundings. It tells you that the water is heading toward a bend a few kilometers away. A regional map shows that the bend belongs to a larger river system heading toward a distant valley. A continental map reveals that the river eventually joins a much larger network. If you ask where the water is going, all three maps can give different answers without any of them being wrong. The cosmic flow around the Milky Way behaves in a similar way. On nearby scales, Virgo matters. Farther out, the Hydra Centaurus region and the structures historically associated with the Great Attractor become prominent. Look over a still larger volume and Shapley becomes important. Turnaround and underdense regions, including the Dipole Repeller, help explain why the flow is unbalanced in the first place. So our galaxy is not following one enormous arrow painted across the universe. It is responding to gravity on many scales at once. The future becomes even more complicated when we remember that the Milky Way is not travelling alone. Andromeda is approaching us. For many years, one of the most widely repeated predictions in astronomy was that the Milky Way and Andromeda would collide in roughly 4 to 5 billion years and eventually merge into a single large galaxy. That scenario was based on measurements showing that Andromeda has a substantial velocity toward the Milky Way and appeared to have relatively little sideways motion. The basic idea is easy to understand. If two massive galaxies are approaching one another almost directly, their gravity accelerates the encounter. As they pass close together, their extended dark matter halos interact. Stars and gas are thrown into new orbits. Gravitational interactions transfer orbital energy. Dynamical friction reduces the relative motion. After one or more close passages, the galaxies can merge. Importantly, a galaxy collision does not mean stars suddenly begin crashing into one another like cars at a busy intersection. Stars are separated by enormous distances compared with their sizes. The dramatic changes come mainly from the changing gravitational field, which reorganizes stellar orbits and can strongly affect gas. For years, simulations made the Milky Way-Andromeda merger sound close to inevitable. Then the measurements improved. A peer-reviewed study published in Nature Astronomy in 2025 incorporated newer Gaia and Hubble measurements, uncertainties in the masses and motions of the major local group galaxies, and the gravitational effects of both the Triangulum Galaxy, M33, and the Large Magellanic Cloud. Instead of finding one certain outcome, the researchers found that roughly half of their modelled systems avoided a Milky Way-Andromeda merger during the next 10 billion years. For the simulated systems that did merge, the median merger time was about 7.6 billion years rather than the older, commonly quoted 4 to 5 billion year timetable. That result was a reminder of how sensitive galactic predictions can be to very small uncertainties. Andromeda is about 2.5 million light-years away. Measuring its sideways motion from Earth is extremely difficult. A tiny change in the estimated transverse velocity can produce a major change after billions of years of orbital evolution. Andromeda also does not move in isolation. M33 pulls on it. The Large Magellanic Cloud pulls on the Milky Way. The Milky Way itself responds to the Large Magellanic Cloud strongly enough that our galaxy's centre of mass is affected. Once those additional motions are included, the future trajectory of the two large galaxies changes. Then, in March 2026, another study revisited the calculation using updated Gaia-based proper motion estimates for Andromeda and M33. That analysis found a much higher Milky Way-Andromeda merger probability, about 90% in its preferred 4-galaxy model, with a median merger time of roughly 6.5 billion years. Yet the authors also stress that the result remains sensitive to the adopted proper motion of Andromeda. Across the range of allowed measurements they examined, the merger probability remained broad enough that they did not regard the final outcome as completely settled. So as things stand, the safest statement is not that the Milky Way definitely will merge with Andromeda, and not that it definitely will avoid Andromeda. A merger currently looks quite plausible, and some of the newest measurements favour it strongly, but the prediction is still being refined. This is one of those cases where getting a better answer requires measuring something almost absurdly small. Astronomers already know Andromeda is coming toward us along our line of sight. The difficult part is determining exactly how much it is moving sideways. If the sideways component is small enough, the encounter becomes much more direct. If it is larger, Andromeda can pass farther from the Milky Way, reducing the effectiveness of dynamical friction and potentially allowing the two galaxies to continue separately for much longer. A change that seems tiny today can decide whether two galaxies merge several billion years from now. Whatever happens between the Milky Way and Andromeda, it will be a local event compared with the much larger flow connected to the Dipole Repeller and Shapley. This distinction matters. If the Milky Way merges with Andromeda, the resulting galaxy will not suddenly stop participating in the larger cosmic motion. The combined system would inherit the motion of the local group through the surrounding large-scale gravitational field. Merging changes what happens inside our local galactic neighborhood. It does not remove the neighborhood from the cosmic web. Think of two boats floating down a river. If the boats drift toward one another, collide, and become tied together, the combined object is still being carried downstream. The local interaction and the larger current are separate levels of motion. The Milky Way and Andromeda may undergo an interaction, while the local group as a whole continues responding to Virgo, Shapley, nearby voids, the Dipole Repeller and other structures. This brings us back to Shapley. If Shapley contributes strongly to our present motion, are we eventually going to reach it? Probably not in the simple sense suggested by the word destination. Shapley lies hundreds of millions of light years away and belongs to a universe whose expansion is accelerating on large scales. Its gravity contributes to peculiar velocities, but that does not mean every galaxy currently moving partly in its direction will eventually fall into it. The difference is the same one we encountered earlier between cosmic expansion and peculiar velocity. A galaxy can be receding because of the expansion of the universe, while simultaneously having an additional peculiar velocity toward a mass concentration. Both can happen at once. At large enough distances, the expansion can dominate the long-term separation, even when gravity produces a measurable local deviation from the Hubble flow. Shapley therefore helps shape our current motion without necessarily becoming the place where the Milky Way eventually arrives. The same applies to the Dipole Repeller in reverse. We are moving away from the repeller in the reconstructed peculiar velocity field, but we should not picture ourselves starting near the middle of a void and now escaping it along a straight route. The underdensity is part of a changing density field. The void itself evolves, its surrounding galaxies move. Cosmic expansion changes distances between unbound structures. Our present velocity tells us about the gravitational imbalance acting across cosmic history, not a permanent travel itinerary. This difference between a velocity and a destination is surprisingly important. If a weather station tells you that the wind is blowing east at 30 km per hour, you know what the air is doing now. You do not automatically know where the same parcel of air will be in 3 weeks. Pressure systems will move, temperatures will change, other winds will redirect it. A galaxy's motion is vastly slower to evolve, but the principle is similar. The present velocity field is a snapshot of a changing gravitational environment. This is why researchers increasingly use simulations when asking about the far future. A reconstructed streamline tells us what the present velocity field looks like. A simulation can allow matter and the gravitational field to evolve together. The 2026 work on the Great Attractor question did exactly this. Instead of simply tracing today's velocity arrows indefinitely, the researchers evolved digital reconstructions of the nearby universe far into the future. In those simulations, the dominant future displacement of the local group was toward the Virgo direction, rather than toward one classical Great Attractor or directly toward Shapley. Even Virgo, however, accounted for at most about 1/3 of the local group's velocity in their analysis. Their main conclusion was that no single structure provides a complete answer to where we are moving. This is quite different from the older idea of one enormous hidden attractor controlling everything. It suggests that asking where is the Milky Way going is a little like asking which one person is responsible for moving a crowded boat when several people are rowing. The river is flowing, the wind is blowing, and someone at the back has quietly stopped paddling. There may be a dominant contribution in one calculation. There may be another dominant contribution on a different scale. The final motion belongs to the whole system. Modern maps based on cosmic flows have made that increasingly clear. A 2023 dynamical analysis using cosmic flows, 4 mapped Laniakea and several other supercluster scale basins through their gravitational velocity fields. It dynamically identified not only Laniakea, but also structures including Shapley, Perseus Pisces, Hercules, Lepus, and Apus. The same work found large repelling regions associated with major voids and suggested that the previously named Dipole Repeller and cold spot repeller may form parts of one still larger underdense entity. That is a useful reminder that our 10-part journey has been dealing with a map that is still improving. The Dipole Repeller is not necessarily a perfectly isolated spherical void with a clean boundary. Shapley is not one compact object. Laniakea is not a solid island. The cosmic web is continuous. Structures connect. Voids merge into larger underdense networks. Filaments feed clusters. Different mapping techniques divide this complicated distribution in different useful ways. The names help us talk about it. Gravity responds to the entire matter field. If we could watch the local group from outside for billions of years, its route would not look like a spacecraft flying past a series of signposts. Nearby galaxies would interact. Some dwarf galaxies would be absorbed. The Large Magellanic Cloud is expected in current models to interact strongly with and eventually merge into the Milky Way. In the 2026 four-body calculation, that merger occurred before the possible Milky Way Andromeda encounter. M33 may likewise strongly interact with Andromeda. Whether the two largest galaxies finally merge depends sensitively on their masses and present motions. At the same time, the larger environment would continue evolving. Virgo would continue shaping flows nearby. Mass would continue gathering into gravitationally bound structures. Voids would become increasingly empty relative to dense regions. The overall expansion would continue separating structures that are not bound strongly enough to resist it. The Milky Way's future is therefore partly local and partly cosmological. Locally, it belongs to a gravitationally interacting group of galaxies. On greater scales, that group participates in the cosmic web. On still greater scales, the universe expands. Those three statements are all true at the same time. This gives us a better way to answer the question we started with. Something is pushing the Milky Way through space, provided we understand what the word pushing means. There is no hidden engine. There is no giant object firing some unknown force at the back of our galaxy. The push comes from an underdense region contributing less gravitational attraction than an average region would. Meanwhile, matter-rich regions in other directions pull more strongly. The result is an imbalance. The local group responds to that imbalance. Our motion relative to the cosmic microwave background is one measurable result. The Great Attractor was an early attempt to locate enough mass to explain the flow. Shapley revealed that important gravitational structure extends much farther. The Dipole Repeller demonstrated that looking only for excess matter misses half of the basic idea. Peculiar velocity surveys then allowed astronomers to reconstruct both the crowded and empty parts of the gravitational landscape. Once those pieces are combined, the Milky Way's speed stops looking like evidence for one mysterious object. It becomes evidence for the cosmic web itself. There is something especially useful about ending with that distinction because it changes the mystery without removing it. At the beginning, the strange part was that our galaxy is moving so quickly. Then the strange part became the Great Attractor, then Shapley, then a gigantic underdensity that appeared to repel us. After following the measurements, none of those things requires unusual physics. Gravity is behaving normally. Galaxies are behaving normally. Voids are behaving normally. The surprising part is simply the scale on which ordinary gravity is operating. A small difference in matter density in the early universe can grow for billions of years. One region becomes filled with clusters. Another becomes a vast void. Hundreds of millions of light-years away, a galaxy containing our Sun acquires part of its motion because of that difference. And we can measure it. We can measure ancient microwave radiation and determine that our local group is not at rest relative to it. We can measure galaxy redshifts. We can estimate distances. We can subtract the smooth expansion of the universe. We can recover peculiar velocities. We can reconstruct the three-dimensional gravitational flow. Then, from a single planet inside a single galaxy, we can work out that one enormous part of the universe contains too much matter, another contains too little, and our entire galactic neighbourhood is moving through the imbalance between them. As for exactly where the Milky Way will be several billion years from now, the answer is still being refined. It may experience a close encounter and merger with Andromeda, a possibility favoured strongly by some of the latest 2026 calculations, but still sensitive to measurements that astronomers are improving. The local group will continue responding to its wider gravitational environment. The present cosmic flow will evolve. The simple idea that we are heading toward one permanent Great Attractor is giving way to a much richer picture in which different structures dominate at different scales, and no single object explains our motion by itself. And right now, while all of that happens, there is no sensation of movement at all. Your room remains where it was, the floor feels stationary, the stars outside appear almost fixed. Yet Earth continues around the Sun. The Sun continues through the Milky Way. The Milky Way moves with the local group, and the local group continues through a gravitational landscape built from clusters, filaments, and enormous regions where much of the expected matter simply is not there. The next time you see the Milky Way stretching across a dark sky, it may help to remember that you're not looking at something suspended motionless above you. You're looking from inside it, and the whole thing is already on its way,